Astronomy often advances by studying unknown. Astronomy often advances by studying the largest and brightest objects in the universe, but some of the most important insights come from examining the smallest and faintest. Galaxies at the extreme low end of size and mass test the limits of how structure forms, how matter behaves under gravity, and how the early universe shaped what exists today. These systems are difficult to detect, challenging to measure, and easy to overlook, yet their implications reach far beyond their modest appearance. XXXV is one such system. Identified through deep observational surveys, it represents one of the smallest known galaxies ever confirmed. With only a sparse population of stars and an extremely low luminosity, XXXV sits at the boundary between galaxies and other stellar systems. This documentary traces what XXXV is, how it was discovered, and why its existence matters for understanding galaxy formation, dark matter, and the minimum conditions required for a galaxy to survive. Defining galaxy at the smallest scale. Before examining 35 itself, it is necessary to establish what astronomers mean by the term galaxy. At familiar scales, galaxies are understood as vast, gravitationally bound systems containing billions of stars, interstellar gas, dust, and large reservoirs of dark matter. This picture applies well to spiral and elliptical galaxies, but becomes progressively less clear as astronomers push towards smaller, fainter, and more weakly populated systems. At these limits, long-standing assumptions about what constitutes a galaxy begin to lose precision. Historically, galaxies were defined observationally rather than physically. Early catalogues relied on visual appearance, size, and brightness. Objects that appeared extended and unresolved were classified as galaxies, while compact, resolved systems were labelled star clusters. This approach worked when observational limits prevented detection of extremely faint systems. As instrumentation improved, these visual criteria became insufficient. Objects once thought to be clusters were revealed to have properties inconsistent with purely stellar systems. At low masses, the distinction between galaxies and star clusters becomes especially ambiguous. Star clusters are gravitationally bound collections of stars, and some globular clusters contain hundreds of thousands of stars within relatively compact volumes. These systems are typically old, chemically uniform, and dominated by the mass of their visible stars. Their internal stellar motions can be explained without invoking unseen mass, and their formation is generally tied to single, short-lived star formation events. Galaxies, in contrast, are believed to form within dark matter halos. Even when they contain very few stars, their total mass can be dominated by dark matter. This distinction became increasingly important with the discovery of ultra-faint dwarf galaxies, some of which contain only a few hundred to a few thousand stars, yet exhibit velocity dispersions that imply masses far exceeding what their luminosity alone would suggest. In these systems, stars trace the gravitational potential but do not define it. As observations expanded, astronomers began identifying systems that defied simple classification. Some objects were as faint and compact as star clusters, but showed kinematic evidence for dark matter. Others were spatially extended, exhibited multiple stellar populations, or showed internal chemical variation inconsistent with a single star-forming episode. These discoveries forced a shift away from appearance-based classification toward physically motivated criteria. Modern definitions of a galaxy emphasize a combination of properties rather than a single defining feature. One key indicator is dark matter dominance. If a system's stellar motions cannot be explained by visible matter alone, it is generally classified as a galaxy. Another indicator is chemical diversity. Galaxies often show a spread in stellar metallicity, implying extended or multiple episodes of star formation. Star clusters, by contrast, tend to be chemically uniform, because they form stars over a short timescale from a well-mixed gas reservoir. Additional factors are sometimes considered. Structural extent can be informative, as galaxies are typically more spatially diffuse than star clusters of similar luminosity. Dynamical stability over long timescales also matters. Systems that remain coherent despite external tidal forces are more consistent with dark matter-dominated halos. No single criterion is decisive, but taken together, these characteristics help distinguish galaxies from clusters at the smaller scales. Despite these guidelines, classification remains uncertain at the extremes. Measuring stellar velocities in ultra-faint systems is observationally difficult, with small sample sizes and large uncertainties. Chemical measurements require high-quality spectra that are often unavailable. As a result, classification relies on converging lines of evidence rather than firm thresholds. This ambiguity is not a failure of definition, but a reflection of physical continuity between different types of bound systems. This uncertainty raises the question of whether a minimum galaxy size exists. Theoretical models suggest that below a certain dark matter halo mass, gas cannot cool efficiently and star formation is suppressed. Cosmic reionization further limits the ability of small halos to retain gas by heating the intergalactic medium and increasing pressure against collapse. Together, these processes imply a lower bound on galaxy formation. However, observational discoveries have repeatedly pushed this boundary downward. Each new ultra-faint dwarf galaxy forces revisions to models that predicted fewer or no galaxies at such small scales. These systems demonstrate that star formation can occur under more restrictive conditions than once assumed, even if only briefly. 35 lies at the extreme edge of this population, making it a critical test case for both observational classification and theoretical limits. Understanding whether 35 qualifies as a galaxy is therefore not a semantic exercise. The classification carries implications for how many galaxies exist, how dark matter behaves on small scales, and how the early universe shaped structure formation. If systems like 35 are genuine galaxies, then the universe is capable of producing and preserving organized structure under conditions once thought insufficient. Defining a galaxy at the smaller scale becomes a question about physics rather than terminology. It asks what combinations of mass, gravity, timing and environment are sufficient to produce a stable, long-lived system. 35 exists precisely where these conditions are most strained and most informative. With this framework in place, the examination of 35 can proceed. Its properties do not merely test definitions, they probe the limits of galaxy formation itself. In doing so, 35 provides a rare opportunity to observe where galaxies cease to be inevitable outcomes of cosmic structure and instead become exceptional survivors. The discovery of 35. The identification of 35 did not occur through targeted observation or prior expectation. Like many ultra-faint galaxies, it emerged from systematic sky surveys designed to map large regions of the sky with unprecedented sensitivity. These surveys were not optimized to find the smallest possible galaxies. Their primary goals were broader, cataloging stellar populations, measuring precise positions and motions, and identifying large-scale structure. The discovery of 35 was therefore incidental, arising as a byproduct of comprehensive data collection rather than a focused search. XXXV first appeared as a subtle statistical signal rather than a clearly resolved object. In wide-field survey data, astronomers noticed a slight clustering of stars whose spatial distribution deviated from known foreground patterns. Individually, the stars were unremarkable. They were faint, sparsely distributed, and easily confused with background stars belonging to the Milky Way's halo. What distinguished them was their collective behavior. When analyzed together, their positions formed a pattern that was unlikely to result from random chance. Detecting such patterns requires careful statistical treatment. Modern surveys generate catalogues containing millions or billions of stars. Within such vast datasets, random alignments are inevitable. Identifying a genuine structure requires demonstrating that the observed clustering exceeds what would be expected from random distributions. For 35, this involved comparing local star counts against surrounding regions and against simulated backgrounds. The excess was small but persistent. Confirming that such a signal represents a real astrophysical object is a cautious and methodical process. The first priority is to eliminate observational artifacts. Variations in detector sensitivity, uneven sky coverage, dust extinction, or data processing effects can all produce artificial overdensities. In the case of 35, astronomers cross-check the signal using multiple datasets collected at different times and with different instruments. The persistence of the clustering across independent observations reduced the likelihood that it was an artifact. Once instrumental explanations were ruled out, attention turned to the properties of the candidate stars themselves. Stellar population analysis became central. The stars associated with 35 showed consistent colours and magnitudes, suggesting a shared distance and evolutionary history. This coherence is critical. Random foreground groupings typically exhibit wide spreads in distance, age, and composition. In contrast, the stars linked to 35 aligned along a narrow sequence when plotted on a colour magnitude diagram, consistent with a single, ancient stellar population. This alignment provided a strong indication that the stars were physically related. Colour magnitude diagrams act as fingerprints for stellar systems, allowing astronomers to distinguish between coincidental alignments and genuine associations. For 35, the diagram indicated old metal-poor stars, a characteristic signature of early formed dwarf galaxies. Distance estimation provided an additional layer of confirmation. By comparing the observed stellar sequence to theoretical models of stellar evolution, astronomers inferred the distance required to produce the measured brightness distribution. XXXV was found to lie far beyond the Milky Way's disk, well outside the region dominated by typical field stars. This placed it firmly in the realm of satellite systems, rather than local stellar substructures. Follow-up observations were essential to strengthen the case. Deeper imaging allowed astronomers to identify additional candidate member stars and refine the system's spatial extent. Even modest increases in depth significantly improved confidence by increasing the number of stars associated with the structure. Spectroscopic observations, where feasible, provided velocity measurements. Although such measurements were limited by the faintness of the stars, even a small sample showing coherent motion helped distinguish 35 from unrelated foreground populations. Velocity coherence is particularly important because it probes gravitational binding. Stars moving together through space imply a shared gravitational potential. For systems as faint as 35, acquiring such data is challenging, but even partial confirmation strengthens classification. Combined with spatial clustering and stellar population coherence, the velocity data supported the interpretation of 35 as a bound system. The designation 35 reflects its inclusion in a broader catalogue of faint galaxies identified through similar survey efforts. The numbering indicates that it is part of an expanding population rather than a singular discovery. However, its extreme faintness and low stellar mass quickly set it apart. Among known systems, 35 ranked near the lower limit of luminosity and stellar content for confirmed galaxies. Importantly, the announcement of 35 was measured rather than sensational. Astronomers emphasized uncertainties, observational limits, and the provisional nature of classification at such extremes. This caution reflects standard practice in observational astronomy, especially when dealing with objects that challenge existing frameworks. The classification of 35 as a galaxy rested on multiple converging indicators rather than a single defining measurement. The discovery process also illustrates a broader transformation in astronomy. Modern discoveries increasingly emerge from data-driven analysis rather than direct visual inspection. Objects like 35 are not found by pointing a telescope and seeing a galaxy. They are found by mining datasets, testing statistical significance, and iteratively refining models. This shift has expanded the observable universe into regimes that were previously inaccessible. XXXV would have been invisible to earlier generations of surveys. Its detection required deep imaging, precise photometry, and sophisticated algorithms capable of identifying structure near the noise floor. Its discovery therefore represents not only the identification of a new galaxy, but also the success of methodological advances in astronomical observation. The emergence of 35 from survey data underscores an important point. The smallest galaxies do not announce themselves through brightness or scale. They reveal themselves only through persistence and coherence across multiple lines of evidence. Their discovery is slow, incremental, and dependent on rigorous elimination of alternative explanations. With 35 confirmed as a distinct system, attention could shift from detection to interpretation. Its existence immediately raised questions about formation, survival, and classification. Why did this system form stars at all? How did it avoid destruction? What does its survival imply about the limits of galaxy formation? These questions extend beyond 35 itself. Each new ultra-faint galaxy reshapes expectations about the low-mass universe. 35, by sitting at the extreme edge of detectability, sharpens those questions and anchors them in observable reality. The chapters that follow build on this foundation, using 35's discovery as a gateway to understanding the smaller scales of cosmic structure. Locating 35 in the cosmic neighborhood. Understanding where 35 exists in relation to other structures is essential to interpreting its significance. Location determines environment, and environment influences how galaxies form, evolve, and survive. For systems as small as 35, even modest gravitational influences from nearby galaxies can shape their history. Establishing its position within the local universe therefore provides context for every physical property that follows. XXXV is not an isolated object drifting through intergalactic space. Distance measurements place it within the broader gravitational influence of the Milky Way, situating it among the population of satellite galaxies that orbit larger hosts. These satellites occupy the extended dark matter halo surrounding the Milky Way, rather than the galactic disk itself. This halo extends far beyond the visible edge of the galaxy, encompassing a region where gravitational forces dominate, despite the absence of dense stellar populations. Satellite galaxies within this halo follow a wide range of orbital paths. Their trajectories are often elongated rather than circular, carrying them through regions of varying gravitational intensity. Over billions of years, these orbits can bring satellites close to the Milky Way's center before sending them back outward. Each passage exposes them to different environmental conditions, including tidal forces, hot halo gas, and interactions with other satellites. Determining the distance to 35 required careful analysis of its stellar population. Astronomers relied on standard stellar markers, particularly the brightness and color of old, low-mass stars at well-understood evolutionary stages. By comparing observed magnitudes with stellar evolution models calibrated in nearby systems, they inferred the system's distance despite the limited number of detectable stars. This placed 35 well beyond the foreground populations of the Milky Way disk, confirming that it is not a chance alignment of nearby stars. Its distance situates it firmly within the Milky Way's satellite system, but not in the innermost regions where tidal forces are strongest. This placement is significant. Satellites closer to the galactic center are more likely to be disrupted over time, losing stars and dark matter through repeated tidal stripping. 35's continued coherence suggests that it has avoided the most destructive regions of the Milky Way's gravitational potential. The position of 35 relative to other known satellites is also informative. It does not lie within a dense cluster of satellites, nor does it appear embedded within a prominent stellar stream associated with a disrupted progenitor. Stellar streams are remnants of galaxies that have been torn apart, leaving elongated trails of stars along their former orbits. The absence of such features around 35 suggests that it is not a recent fragment of a larger system, but rather an object that has retained its identity over long timescales. This interpretation is reinforced by its structural symmetry. Systems undergoing active tidal disruption often show distorted shapes, gradients in stellar density, or extended tails. XXXV appears relatively regular, consistent with a galaxy that has experienced environmental influence without catastrophic alteration. This balance between exposure and survival provides insight into the conditions under which ultra-faint galaxies can persist. The spatial distribution of Milky Way satellites as a whole is a topic of active research. Some satellites appear to align along planes or preferred directions, while others show more isotropic distributions. These patterns have implications for dark matter models and for the history of satellite accretion. 35 adds a valuable data point at the faint end of this distribution. While a single object cannot resolve broader debates, each additional satellite refines statistical understanding of how these systems are arranged. Motion provides another layer of context. Measuring precise velocities for such faint systems is challenging, but available spectroscopic data indicate that the stars associated with 35 share a common motion. This coherence supports its classification as a bound system. Its overall velocity relative to the Milky Way suggests long-term association rather than recent capture. This implies that 35 has been orbiting within the halo for a substantial fraction of cosmic time. Long-term residence within the Milky Way's halo carries consequences. Satellites moving through this environment encounter hot, diffuse gas that can strip away their own gas reservoirs through ram pressure interactions. For a system as small as 35, such stripping would be highly efficient. Its present lack of detectable gas is therefore consistent with expectations for a long-term satellite. Importantly, gas loss does not necessarily imply destruction. While star formation ceases, the stellar and dark matter components can remain bound. Tidal effects operate alongside gas stripping. Even when gas is removed, a sufficiently dense dark matter halo can preserve stellar structure. 35's survival implies that its halo was dense enough to resist complete disruption. This resilience offers clues about the minimum halo properties required for longevity in hostile environments. Locating 35 within the Milky Way's halo also highlights its role as a tracer of small-scale structure. Satellite galaxies serve as test particles for mapping the galaxy's gravitational potential and for testing predictions of dark matter distribution. Ultra-faint satellites like 35 are particularly sensitive probes because their dynamics are dominated by dark matter rather than baryonic mass. In this context, 35 occupies a critical observational niche. It is close enough to allow detailed study of individual stars, yet faint enough to challenge detection limits. Its existence confirms that extremely small galaxies can survive within the gravitational sphere of influence of a massive host, provided they occupy suitable orbits and possess sufficiently robust dark matter halos. By establishing where 35 resides, astronomers gain insight into both its past and its future. Its location explains its gas loss, its limited evolution, and its preservation as a coherent system. It also suggests that its future will be similarly quiet, characterized by continued orbiting rather than dramatic transformation. With 35's position in the cosmic neighborhood defined, its physical properties can be interpreted within an environmental framework. Location connects formation, survival, and present appearance. Having established that framework, attention can now turn to the challenge of extracting physical information from a galaxy that exists at the very edge of detectability. Measuring a galaxy that barely exists. Once 35 was confirmed as a real astrophysical system, the next challenge was determining its basic physical properties. Measuring any galaxy requires estimating its size, luminosity, mass, and structure. For 35, each of these measurements pushes observational techniques to their limits. Its faintness and sparse stellar population mean that standard methods must be applied with unusual care, and uncertainty becomes an inherent component of every result, rather than a margin to be minimized. The most immediate property to establish is size. For bright galaxies, size can be measured by tracing continuous light profiles that fade smoothly into the background. XXXV does not emit enough light for this approach. Instead, astronomers infer its extent by mapping the spatial distribution of its member stars. Each star associated with 35 becomes a discrete data point. By examining how stellar density decreases with distance from the system's center, researchers estimate a characteristic radius that defines the galaxy's spatial scale. This method introduces unavoidable ambiguity. With so few stars, statistical fluctuations can significantly influence inferred structure. A single misidentified star can distort size estimates if it lies far from the center. To mitigate this, astronomers employ probabilistic membership models. Each star is assigned a likelihood of belonging to 35, based on position, color, brightness, and consistency with the system's stellar population. Size estimates are therefore expressed as probability-weighted distributions rather than sharp boundaries. Luminosity presents a similar challenge. 35 emits so little total light that it cannot be measured as an integrated source. Instead, luminosity is reconstructed by summing the estimated contributions of individual stars and correcting for stars that fall below detection limits. This correction depends on assumptions about the stellar population, including its age, metallicity, and the initial mass function. Because the total stellar mass is so small, even minor changes in these assumptions can produce noticeable shifts in inferred luminosity. Despite this sensitivity, independent analyses converge on the same conclusion. 35 is among the faintest galaxies ever confirmed. Its total luminosity is comparable to that of a single luminous star in the Milky Way. This places it far below classical dwarf galaxies and even below many ultra-faint systems identified earlier. The agreement across different datasets and modelling approaches reinforces confidence that 35 represents a genuine extreme rather than an artifact of methodology. Estimating mass is more demanding still. The visible stars contribute negligible mass, so the system's total mass must be inferred from stellar motions. By measuring the velocities of individual stars, astronomers estimate the gravitational potential required to keep the system bound. In larger galaxies, dozens or hundreds of stellar velocities can be measured. In 35, only a handful are accessible, making each measurement disproportionately influential. Even so, the available data indicate that visible matter alone cannot account for the system's stability. The inferred gravitational binding exceeds what the stars could produce by a large margin, implying the presence of a dominant dark matter halo. While uncertainties remain large, the qualitative conclusion is robust. 35 behaves dynamically like a dark matter-dominated galaxy, rather than a star cluster. Structural measurements add further constraints. 35 shows no evidence of rotation, disks, or internal substructure. Its stellar distribution appears diffuse and roughly spherical, consistent with pressure-supported systems. Confirming this simplicity requires careful removal of foreground contamination, as Milky Way halo stars can mimic member stars at faint magnitudes. Foreground contamination complicates every measurement. Extensive modelling of the Milky Way's stellar population is required to statistically subtract unrelated stars. Errors in this modelling propagate directly into size, luminosity, and mass estimates. As a result, astronomers emphasize ranges and confidence intervals rather than precise values. Distance uncertainty compounds these effects. A small error in distance affects inferred luminosity, physical size, and mass simultaneously. Although 35's distance is reasonably constrained, it remains a source of systematic uncertainty that cannot be eliminated entirely. Despite these limitations, a coherent picture emerges. 35 is extremely small, extremely faint, and overwhelmingly dominated by unseen mass. Its measured properties are internally consistent and align with theoretical expectations for a galaxy operating at the lowest viable mass scale. The difficulty of measuring 35 explains why such systems were identified only recently. Earlier surveys lacked the depth, precision, and statistical sophistication required to characterize galaxies at this limit. XXXV exists observationally because modern astronomy has reached the threshold where inference is possible even when direct signals are minimal. Measuring a galaxy that barely exists forces astronomers to confront the limits of observation itself. It requires treating uncertainty as information rather than error, and combining sparse data with rigorous statistical frameworks. In this sense, 35 is not only a galaxy under study, but a benchmark for how far observational cosmology can be pushed. With its basic properties constrained, attention can now turn to what its minimal stellar content reveals about galaxy formation and the fundamental condition required for a galaxy to exist at all. Stellar content. How few stars can a galaxy have? The defining feature of 35 is not its shape, distance, or motion, but the remarkable scarcity of its stars. At first glance, this scarcity raises a fundamental question. How few stars can a system contain and still qualify as a galaxy? Answering this question requires careful examination of 35's stellar population and comparison with other known systems at the boundary between galaxies and star clusters. In most galaxies, stars dominate observational appearance. Even dwarf galaxies typically contain millions of stars. In contrast, 35 contains only a small number of detectable stars, likely numbering in the hundreds or fewer. This places it among the sparsest stellar systems ever classified as a galaxy. The majority of its mass, inferred from dynamics, is not associated with stars at all. The stars that are present are predominantly old. Their colours and magnitudes are consistent with ancient, low-mass stars that formed early in the universe's history. There is little evidence for younger stellar populations. This suggests that star formation in 35 occurred during a brief early period and then ceased. The absence of recent star formation is consistent with the lack of detectable gas and the system's low overall mass. Colour magnitude diagrams provide insight into this history. When the observed stars are plotted according to brightness and colour, they trace a narrow sequence consistent with a single, old stellar population. There is no indication of multiple generations of stars with differing ages. This contrasts with larger galaxies, which often show complex stellar populations reflecting extended or episodic star formation. The small number of stars also affects how reliably properties can be measured. Each individual star carries disproportionate weight in statistical analyses. Removing or misclassifying even a few stars can alter inferred properties such as age distribution or metallicity. As a result, astronomers apply conservative criteria when identifying member stars, prioritizing reliability over completeness. Comparisons with globular clusters are unavoidable. Some globular clusters contain more stars than 35 and are similarly compact. However, globular clusters differ in key ways. Their stars typically share nearly identical chemical compositions, indicating formation in a single burst from well-mixed gas. In contrast, the limited data available for 35 suggests a modest spread in metallicity, implying some level of chemical evolution rather than a single formation event. The presence of dark matter further distinguishes 35 from star clusters. Stellar motions imply that the gravitational potential binding the system cannot be explained by the stars alone. This means that, despite its sparse stellar content, 35 resides within a dark matter halo. The stars serve primarily as traces of a much larger unseen structure. This realization shifts how stellar content is interpreted. In systems like 35, stars are not the dominant component, but rather the visible residue of a larger gravitational framework. The galaxy's identity is therefore defined less by the number of stars it contains, and more by the structure that holds those stars together. The scarcity of stars also reflects the inefficiency of star formation at small scales. In low-mass dark matter halos, gas cooling is difficult, and external processes such as cosmic reionization can suppress star formation entirely. XXXV appears to represent a case where these suppressive effects nearly succeeded, leaving behind only a minimal stellar imprint. Understanding how 35 formed even this small number of stars informs models of galaxy formation. It suggests that the threshold for star formation is not absolute. Under the right conditions, even extremely small halos can briefly form stars before environmental factors halt the process. The existence of 35 demonstrates that a galaxy does not require a rich stellar population to persist. A handful of stars can suffice, provided they are embedded within a stable gravitational potential. This challenges intuitive associations between galaxies, and large numbers of stars and forces a re-evaluation of what constitutes the minimal expression of a galaxy. As the smallest known galaxy, 35 illustrates that stellar content alone is an incomplete measure of galactic identity. Its stars are few, faint, and ancient, yet they reveal a system shaped by the same physical principles that govern far larger galaxies. This makes 35 a valuable reference point for understanding the lower limits of galaxy formation and survival. Metallicity and chemical simplicity. Beyond the number of stars, the chemical composition of those stars provides critical insight into the nature of 35. In astronomy, metallicity refers to the abundance of elements heavier than hydrogen and helium within stars. These elements are produced through stellar nucleosynthesis and dispersed into surrounding gas by supernova explosions and stellar winds. As a result, metallicity serves as a record of how much star formation and chemical processing a system has experienced over time. In large galaxies, metallicity tends to increase steadily as generations of stars form and die. Each cycle enriches the interstellar medium, allowing subsequent stars to incorporate heavier elements. Even relatively small dwarf galaxies often show evidence of this gradual enrichment. 35, however, occupies a far more chemically primitive regime. Spectroscopic observations of its stars indicate extremely low metallicity. The stars contain only trace amounts of heavy elements, suggesting that they form from gas that had undergone very little prior chemical processing. This places 35 among the most chemically simple galaxies known. Such simplicity implies that star formation occurred early and ceased before multiple enrichment cycles could take place. The low metallicity is consistent with the old age of 35's stellar population. In the early universe, heavy elements were scarce. The first stars formed from nearly pristine hydrogen and helium, left over from the Big Bang. Only after those stars ended their lives did heavier elements become more widespread. 35 appears to preserve this early chemical state, making it a fossil record of early cosmic conditions. Chemical simplicity also constrains the duration of star formation. If 35 had sustained star formation over extended periods, even at low rates, metallicity would have increased measurably. The absence of such enrichment suggests that star formation was brief and inefficient. Whatever gas 35 initially possessed was either consumed quickly or removed before further stars could form. The relationship between metallicity and galaxy mass provides additional context. There is a well-established correlation in which lower mass galaxies tend to have lower metallicities. This is partly because their shallow gravitational potentials struggle to retain enriched gas expelled by supernovae. 35 lies at the extreme low end of this relationship. Its metallicity is not merely low relative to large galaxies, but unusually low even compared to other ultra-faint dwarfs. This extreme chemical simplicity reinforces the interpretation that 35 formed stars under highly constrained conditions. Its dark matter halo was likely just massive enough to allow limited gas cooling and star formation before external influences intervened. Cosmic rayonization, which heated intergalactic gas and suppressed cooling in small halos, may have played a decisive role in halting further star formation. Metallicity measurements also help distinguish 35 from star clusters. Globular clusters often exhibit narrow metallicity distributions, reflecting a single formation event. While 35's data are limited, the available evidence suggests at least a modest spread in stellar metallicity. Even a small spread indicates that the system experienced more than one enrichment episode, consistent with galactic rather than cluster-like behavior. Chemical composition further informs theories of early galaxy formation. Systems like 35 suggest that some galaxies formed and chemically evolved in isolation, largely unaffected by later cosmic enrichment. They provide empirical anchors for models of the first generations of star formation and the conditions that allowed or suppressed continued growth. The simplicity of 35's chemistry also highlights observational challenges. Measuring metallicity in such faint systems requires long exposure times and careful analysis. Each star contributes disproportionately to the overall picture. Despite these challenges, the consistency of low metallicity measurements across multiple ultra-faint galaxies supports the reliability of the conclusions. 35's chemical profile strengthens its classification as a galaxy and clarifies its place in cosmic history. It represents a system that formed early, evolved briefly, and then remained largely unchanged for billions of years. Its stars carry a chemical signature that predates much of the universe's later complexity. By preserving such a primitive composition, 35 offers a rare window into early conditions that are otherwise difficult to access. Its metallicity is not just a property, but a record. It tells a story of limited opportunity, early formation, and long-term survival at the edge of what galaxy formation allows. With its stellar content and chemical simplicity established, the next step is to examine the dominant component that holds 35 together: dark matter. Dark matter dominance. While 35 stars are sparse and faint, they do not define the system's true mass. The dominant component shaping the galaxy's structure and evolution is dark matter. In systems like 35, dark matter is not a secondary influence, but the primary framework within which everything else exists. Understanding this dominance is essential to understanding why such a small galaxy can persist at all. Dark matter does not emit or absorb light, making it invisible to telescopes. Its presence is inferred through gravitational effects. In galaxies, this is most commonly done by measuring how stars move within the system. If stellar motions exceed what visible matter alone can explain, additional mass must be present. In 35, the observed stellar velocities indicate a gravitational potential far deeper than its tiny stellar mass would produce. Even with limited velocity data, the conclusion is difficult to avoid. The stars of 35 move as though embedded in a massive halo. The ratio of total mass to visible light is extremely high, far exceeding that of larger galaxies. This mass-to-light ratio places 35 among the most dark matter-dominated systems known. In practical terms, the galaxy is almost entirely dark matter, with stars serving as minor traces of a much larger structure. This dominance explains how 35 survives despite its fragility. Without dark matter, the gravitational binding provided by its few stars would be insufficient to hold the system together against external perturbations. Encounters with the Milky Way's tidal field would quickly disperse it. The presence of a dark matter halo provides the stability necessary for long-term survival. Dark matter also plays a central role in the galaxy's formation. In current cosmological models, galaxies form within dark matter halos that collapse first under gravity. Gas then falls into these halos, cools, and forms stars. For 35, the halo appears to have been just massive enough to initiate this process, but not massive enough to sustain it for long. The result is a galaxy with minimal stellar output, but a substantial dark matter core. The extreme dark matter dominance of 35 makes it particularly valuable for testing dark matter theories. Because baryonic processes such as star formation and feedback are minimal, their complicating effects are reduced. This allows astronomers to study dark matter behavior in a relatively clean environment. The internal dynamics of 35 provide constraints on how dark matter clusters and distributes itself at the smallest galactic scales. Different dark matter models predict different outcomes for such systems. Cold dark matter models suggest that many small halos should exist, though not all should form stars. Warm or self-interacting dark matter models often predict fewer small halos or altered internal structures. The existence and properties of 35 therefore inform debates about which models best describe reality. The density profile of 35's dark matter halo is of particular interest. Some models predict steep central concentrations, while others predict flatter cores. Observationally, distinguishing between these possibilities is difficult, especially with limited stellar data. But even rough constraints help refine theoretical expectations. Dark matter dominance also affects how 35 responds to its environment. A dense halo can shield the stellar component from tidal disruption, allowing the galaxy to survive close passages around larger hosts. At the same time, the shallow potential relative to larger galaxies makes 35 sensitive to processes like gas stripping, which likely contributed to its early cessation of star formation. In a broader context, 35 exemplifies the idea that galaxies are not defined by their stars alone. At the smaller scales, stars become optional components rather than defining ones. What persists is the dark matter structure, with stars marking where baryonic processes briefly succeeded. This perspective challenges intuitive notions of what a galaxy is. 35 shows that a galaxy can exist primarily as a dark matter object, with only a minimal luminous footprint. Such systems expand the known range of galactic forms and highlight the importance of dark matter in shaping the universe. By studying 35's dark matter dominance, astronomers gain insight not only into a single galaxy, but into the fundamental scaffolding of cosmic structure. It is within this invisible framework that the smallest galaxies endure, preserving evidence of conditions that prevailed when the universe was young. 35 versus star clusters. As astronomers pushed toward the faintest detectable systems, one question became unavoidable. How can a system like 35 be confidently identified as a galaxy rather than a star cluster? This distinction is not cosmetic. It carries implications for galaxy formation theory, dark matter physics, and the census of cosmic structure. 35 seats precisely where the traditional boundary between galaxies and star clusters becomes most difficult to draw. Star clusters are among the oldest known stellar systems. Globular clusters, in particular, can contain tens or hundreds of thousands of stars packed into relatively compact regions. They are gravitationally bound, long-lived, and often nearly spherical. At first glance, a sparse system like 35 might appear to be a weak or disrupted cluster, rather than a galaxy. The difference emerges only through careful physical analysis. One of the most important distinctions lies in mass distribution. In star clusters, nearly all of the gravitational binding comes from the stars themselves. Their internal motions can be explained by the visible stellar mass. In 35, this is not the case. The observed stellar velocities require far more mass than the stars can provide. This excess mass is attributed to dark matter, a component that star clusters are not thought to possess in significant amounts. Chemical composition provides another line of separation. Star clusters generally form in a single, relatively brief episode from chemically well-mixed gas. As a result, their stars tend to share very similar metallicities. Galaxies, even small ones, often show evidence of chemical variation, reflecting extended or multiple periods of star formation. Although the stellar sample in 35 is limited, available measurements suggest a modest spread in metallicity, consistent with galactic rather than cluster-like behavior. Structural properties also differ. Star clusters are typically compact, with steep density profiles and well-defined boundaries. 35 appears more diffuse. Its stars are spread over a larger volume relative to their number, and its density declines gradually with radius. This extended structure is more consistent with a dark matter-supported system than with a purely stellar cluster. Dynamics further reinforce the distinction. Star clusters often show signs of mass segregation, where heavier stars sink toward the center over time. This process depends on stellar interactions and relaxation timescales. In a system as low density as 35, relaxation times are extremely long, and the influence of dark matter dominates stellar motion. The absence of clear mass segregation aligns with expectations for a galaxy rather than a cluster. Environmental history provides additional context. Many star clusters are associated with larger galaxies and can be stripped, accreted, or disrupted over time. While 35 is also a satellite of the Milky Way, its survival appears to depend on a dark matter halo that shields it from tidal forces. Without such protection, a cluster with similar stellar content would likely have been dispersed. The comparison is not merely academic. Misclassifying systems like 35 would distort counts of both galaxies and star clusters. It would also affect interpretations of dark matter distribution and the efficiency of star formation in small halos. Each confirmed galaxy at this scale strengthens the case that dark matter halos can host stars even under extreme conditions. XXXV therefore occupies a category that star clusters cannot fill. Its stars alone would not define it as a galaxy, but its gravitational behavior does. This distinction highlights a shift in how galaxies are identified at the smaller scales. Visual richness gives way to dynamical evidence. The comparison also clarifies why the smallest galaxies are so difficult to find. They do not announce themselves through brightness or size. They reveal themselves only through subtle patterns in motion, chemistry, and structure. 35 exemplifies this challenge and demonstrates why modern surveys and careful analysis are essential. By contrasting 35 with star clusters, astronomers sharpen the criteria used to define galaxies at the edge of detectability. The differences are not matters of degree, but of underlying physics. XXXV is held together not by its stars, but by an invisible framework that marks it as a true galaxy. This distinction prepares the way for examining how such a fragile system can survive within the gravitational influence of a much larger host. Survival against galactic forces. For a system as small and faint as 35, survival is not guaranteed. Orbiting within the gravitational influence of a much larger galaxy exposes it to forces that can strip stars, distort structure, or dissolve the system entirely. Understanding why 35 still exists requires examining how it has interacted with its environment over billions of years and what conditions have allowed it to persist. The primary external threat to a small satellite galaxy is tidal force. As 35 moves through the Milky Way's gravitational field, differential forces act across its extent. Stars on the side closer to the Milky Way experience a stronger pull than those on the far side. If these forces exceed the internal binding of the system, stars can be pulled away, forming streams or dispersing into the halo of the host galaxy. Many satellite systems show evidence of this process, including elongated shapes and trailing stellar debris. XXXV shows little sign of such disruption. Its stellar distribution appears relatively regular, without obvious tidal tails or asymmetries. This suggests that either its orbit avoids the regions of strongest tidal stress, or that its internal binding is sufficient to resist stripping. The latter possibility points again to the importance of its dark matter halo. Even a modest dark matter mass can significantly deepen the gravitational potential, providing resilience against external forces. Orbital history plays a critical role. Satellites that pass close to the Milky Way's centre experience repeated strong tidal encounters, increasing the likelihood of disruption. In contrast, satellites on wider or more circular orbits encounter weaker tidal forces. While precise orbital parameters for 35 are difficult to measure, its intact structure implies that it has avoided the most destructive trajectories over cosmic time. Another environmental influence is ram pressure stripping. As 35 moves through the hot, diffuse gas that fills the Milky Way's halo, this medium can exert pressure on any gas within the galaxy, pushing it out. For small systems with shallow gravitational potentials, this process can remove gas efficiently, shutting down star formation. 35's lack of detectable gas is consistent with such stripping. However, gas loss alone does not destroy a galaxy. It halts growth, but leaves the stellar and dark matter components intact. Encounters with other satellites also factor into survival. In dense satellite populations, close interactions can perturb orbits and enhance tidal stripping. 35's apparent isolation from major satellite groupings reduces the likelihood of such interactions. This relative solitude may have contributed to its long-term stability. Internal processes are equally important. Systems with high stellar densities can experience internal dynamical heating that gradually expands and weakens the structure. 35's extremely low stellar density minimizes these effects. With few stars and long relaxation times, internal evolution proceeds slowly, preserving the initial configuration. The balance between fragility and resilience defines 35's existence. Its stars alone would be insufficient to withstand the Milky Way's influence. Its dark matter halo provides the necessary binding, while its orbital history limits exposure to destructive forces. Together, these factors create a narrow window in which a galaxy this small can survive. The broader population of small galaxies. The ones observed today are likely survivors of a larger initial population, filtered by tidal destruction and environmental effects. Studying 35 helps identify which conditions favour survival at the smallest scales. These insights inform models of satellite galaxy evolution and help explain why the observed population differs from theoretical expectations. In surviving against galactic forces, 35 preserves a record of early cosmic structure. Its continued existence allows astronomers to study conditions that prevailed when the universe was young, and to test theories about how the smallest galaxies endure in hostile environments. 35 as a fossil of the early universe. XXXV is not simply small, it is old. Its significance lies in the fact that it appears to have changed very little since the earliest epochs of galaxy formation. In this sense, 35 functions as a fossil, preserving physical conditions that were common in the young universe but are now rare. Understanding its age and evolutionary stagnation is central to understanding why it matters scientifically. The stellar population of 35 is dominated by old stars. Color magnitude diagrams indicate that most of its stars formed more than 10 billion years ago, during a period when the universe was still assembling its first generations of galaxies. There is little evidence for prolonged or repeated star formation. This sharply contrasts with larger galaxies, which undergo multiple star-forming episodes driven by mergers, gas accretion, and internal recycling. The lack of younger stars suggests that 35 ceased forming stars early. One likely cause is cosmic reionization. When the first stars and galaxies ignited, they flooded the universe with high-energy ultraviolet radiation. This radiation heated intergalactic gas and made it difficult for small dark matter halos to retain or accrete baryonic matter. For galaxies as small as 35, reionization may have permanently shut down star formation by removing or heating their gas reservoirs. If this is the case, 35 represents a class of galaxies that formed before or during reionization and then effectively froze in time. Its stellar content reflects the chemical and dynamical conditions of that era. The stars within it contain low abundances of heavy elements, indicating minimal chemical enrichment. Each star carries information about the earliest supernovae and nucleosynthesis processes. The absence of internal evolution also matters dynamically. In larger galaxies, repeated star formation and feedback events reshape structure over time. Gas inflows deepen central potentials, while outflows can redistribute matter. 35 lacks these processes. Its structure today likely resembles its structure shortly after formation, aside from gradual tidal influences. This makes it a cleaner system for testing theoretical models of early galaxy assembly. XXXV also provides insight into the minimum conditions required for galaxy formation. Its existence demonstrates that a dark matter halo of extremely low mass can still host star formation, albeit briefly. This challenges simple thresholds used in simulations and suggests that star formation efficiency in the early universe may have been more stochastic than previously assumed. As a fossil, 35 helps bridge theory and observation. Cosmological simulations predict large numbers of small, dark matter halos forming early, but many should never form stars. Others should form stars briefly and then fade. Observed systems like 35 provide rare examples of the latter category. They validate aspects of hierarchical structure formation while highlighting where models must be refined. Importantly, 35 is not unique in principle, but systems like it are difficult to detect. Its discovery implies that other similar fossils may exist, hidden by distance or low surface brightness. Each such system offers an independent snapshot of early conditions, allowing astronomers to compare and cross-check models of reionization, feedback, and dark matter behavior. The fossil nature of 35 also reframes its smallness. Rather than being an underdeveloped galaxy, it is better understood as a relic that completed its evolutionary path early. It did not fail to grow. Growth simply ceased when the universe changed around it. In this way, 35 records a transition in cosmic history. By studying 35, astronomers gain access to a period otherwise inaccessible. Most galaxies have overwritten their early histories through continued activity. XXXV has not. Its stars, structure and dynamics act as a preserved imprint of the early universe, making it one of the most valuable laboratories for understanding how the smallest galaxies first emerged and why some of them survived unchanged to the present day. What 35 reveals about dark matter at the smallest scales. Among the most important reasons 35 draws scientific attention is what it reveals about dark matter. At the scale of large galaxies, dark matter is inferred through rotation curves, lensing, and large-scale structure. At the scale of 35, dark matter is no longer a background component. It is the dominant structural element. Understanding how 35 exists at all requires understanding how dark matter behaves in the smallest gravitational systems capable of hosting stars. Measurements of 35's stellar motions indicate that its visible matter contributes only a tiny fraction of its total mass. The velocities of its stars are far too high to be explained by the gravitational pull of the stars alone. This implies the presence of a dark matter halo outweighing the stellar component by factors of hundreds or even thousands. Few known galaxies are as dark matter dominated as 35. This extreme dominance makes 35 a critical test case for dark matter models. In standard cold, dark matter theory, small halos form early and merge into larger systems over time. Many survive as satellites, but simulations predict far more small halos than observed galaxies. This discrepancy is known as the missing satellites problem. Systems like 35 may represent the faint end of the observable population, suggesting that some missing satellites exist, but are simply difficult to detect. The internal structure of 35 also matters. Cold, dark matter simulations predict steep central density cusps in halos, while some observations of dwarf galaxies suggest flatter cores. Determining whether 35 has a cusp or a core is challenging due to its faintness, but even limited constraints are valuable. If 35 shows evidence of a core, it could indicate that either baryonic processes altered the dark matter distribution early on, or that dark matter has properties beyond the simplest, cold, collisionless model. Because 35 experienced very little star formation, baryonic feedback effects should be minimal. This makes it a cleaner probe of dark matter physics than larger dwarfs where supernova-driven outflows can reshape halos. If a core exists in 35 despite minimal feedback, it would be difficult to explain within standard models. Conversely, a cusp-like profile would strengthen the case that feedback is responsible for cores seen elsewhere. Alternative dark matter theories are also informed by systems like 35. Warm dark matter models predict fewer low-mass halos and smoother structures. Self-interacting dark matter models predict cores even in small systems. Each scenario leaves distinct imprints at the scale of ultra-faint galaxies. XXXV provides one of the few environments where these differences may be observable without strong contamination from baryonic physics. The survival of 35 further constrains dark matter properties. If dark matter were too warm or too strongly interacting, small halos might evaporate or fail to form stars entirely. 35's existence sets a lower bound on halo stability and formation efficiency. Any viable dark matter model must allow objects of this scale to form, retain stars, and persist over cosmic time. There is also a cosmological implication. If galaxies like 35 are common but faint, they may collectively contribute to processes such as reionization or the buildup of the Milky Way's stellar halo. Their dark matter halos would have merged into larger structures, while their stars would remain as fossil traces. Understanding their abundance affects how mass assembled in the early universe. XXXV therefore acts as a microscope for dark matter physics. Large galaxies average over countless processes and histories. XXXV strips the problem down to essentials: gravity, dark matter, and a small population of stars formed early. Its simplicity is its strength. In this sense, 35 does not merely occupy the lower end of the galaxy mass scale. It defines it. It shows how small a galaxy can be while still forming stars and remaining bound. Any theory of dark matter and structure formation must pass through this narrow gate. 35 stands as one of the clearest indicators that dark matter governs cosmic structure all the way down to the smallest observable galactic scales. Limits of star formation in ultra-small galaxies. The existence of 35 highlights a fundamental constraint in galaxy formation. Star formation does not scale smoothly with halo size. Instead, it appears to switch on and off across narrow physical thresholds. Ultra-small galaxies like 35 occupy the regime where these thresholds dominate outcomes. Their properties reveal not why star formation is inefficient, but why it often fails entirely. Star formation begins with gas accumulation. A dark matter halo must first capture baryonic gas from its surrounding. In the early universe, this gas was nearly pristine, composed almost entirely of hydrogen and helium. Cooling mechanisms were limited. Without heavy elements, gas relied primarily on molecular hydrogen to radiate energy and collapse. This process was fragile. Even modest ultraviolet radiation could destroy molecular hydrogen and halt cooling. For a halo the size of 35, this vulnerability was critical. Its gravitational potential was shallow, meaning gas could escape easily once heated. Early star formation required a narrow window in which gas collapsed before external radiation fields intensified. If collapse occurred too late, reionization would prevent it entirely. If it occurred too early, internal feedback could still disrupt it. Evidence suggests that 35 formed stars briefly during this narrow window. Its stellar population is old and metal-poor, consistent with formation before or during cosmic reionization. The absence of younger stars indicates that this window closed quickly and permanently. Once star formation stopped, it never resumed. Reionization played a central role in this outcome. As the first luminous sources formed, Ultraviolet photons ionize neutral hydrogen throughout the universe. Ionized gas is hotter and more resistant to gravitational collapse. Large galaxies retained gas despite this heating. Small halos did not. For systems like 35, reionization effectively raised the minimum mass required for star formation above their scale. Gas loss further compounded the problem. Even if some gas remained bound after reionization, internal feedback posed another barrier. Massive stars live short lives and end as supernovae, releasing enormous energy. In large galaxies, this energy is distributed across vast gas reservoirs. In ultra-small galaxies, the same energy can unbind most of the remaining gas. In 35, only a small number of supernovae would have been sufficient to evacuate gas entirely. Once expelled, gas would not return. The surrounding environment lacked dense reservoirs from which the galaxy could accrete new material. Its orbit within the Milky Way's halo likely exposed it to additional heating and stripping, further preventing gas reacquisition. This sequence explains the abruptness of star formation cessation. 35 did not gradually exhaust its gas. It lost the ability to form stars in a relatively short period. Afterward, it entered a long phase of passive evolution, dominated by stellar aging and slow dynamical processes. The efficiency of star formation in 35 was therefore extremely low. Only a tiny fraction of its available baryons were converted into stars. This inefficiency is not unusual at small scales. Simulations predict that most low-mass halos never form stars at all. 35 represents a rare case where star formation occurred just enough to leave an observable trace. This rarity has implications for how the faint galaxy population is interpreted. Observed ultra-faint galaxies are not typical representatives of small halos. They are survivors that crossed formation thresholds under favourable conditions. The majority of similar halos likely remain dark and undetectable. The limits observed in 35 also challenge simplified models of star formation. Many models assume that star formation efficiency declines smoothly with halo mass. Systems like 35 suggest a more discontinuous behaviour. Below certain thresholds, star formation becomes stochastic, sensitive to timing, environment and feedback, rather than mass alone. Metallicity further constrains star formation. Low metal content reduces cooling efficiency, increasing the minimum density required for collapse. In 35, metallicity remained low throughout its star-forming period. This limited the formation of subsequent stellar generations and reinforced early shutdown. The absence of gas today confirms this history. Observations detect no neutral or molecular gas associated with 35. This is consistent with early removal and long-term inability to replenish supplies. Unlike larger galaxies, 35 lacks internal recycling. Stellar mass loss from evolved stars contributes negligible amounts of gas, insufficient to restart star formation. Environmental effects reinforce these internal limits. As a satellite of the Milky Way, 35 resides in a hot gaseous halo. Any remaining gas would be subject to ram pressure stripping. Even weak pressure is effective against shallow gravitational potentials. Over time, this ensures that gas-free systems remain gas-free. The interplay between internal and external suppression creates a one-way path. Once star formation stops in an ultra-small galaxy, conditions rarely allow reversal. XXXV exemplifies this irreversible transition. It moved from marginal star formation to permanent quiescence early in cosmic history. This behavior explains why the smallest galaxies are uniformly old. Ultra-faint systems show little evidence of recent star formation. Their histories are compressed into the earliest epochs. Later, cosmic evolution bypassed them, favouring larger systems with deeper potentials. XXXV therefore marks a lower boundary for luminous galaxies. Below its scale, halos may exist, but they fail to form stars. This boundary is not fixed by mass alone. It depends on timing relative to reionization, local radiation fields, and early feedback events. 35 happen to form stars before these barriers fully emerge. Understanding these limits refines models of galaxy formation. It clarifies why simulations predict many halos that remain unseen. It also explains why observed small galaxies share similar properties. Despite varied environments, they are products of the same narrow formation window. 35's star formation history is not an anomaly, but an endpoint. It represents the smallest systems capable of briefly participating in cosmic star formation. Its silence since then is not a failure, but a natural outcome of physical limits imposed by gravity, radiation, and feedback. By studying 35, astronomers identify where star formation ends. This boundary shapes the visible universe as much as the processes that create stars. It determines which halos light up the sky and which remain dark. 35 stands at this boundary, preserving evidence of how narrow the path to luminosity can be. Its existence confirms that star formation at the smallest scales is not guaranteed. It must occur early, rapidly, and under favourable conditions. Once lost, the opportunity does not return. This realization deepens understanding of why the universe contains so many dark structures and so few tiny galaxies. The limits observed in 35 therefore extend beyond a single object. They define a regime of galaxy formation where absence is more common than presence. Studying that regime reveals as much about cosmic structure as studying the largest and brightest galaxies. Orbital history and long-term stability. The continued existence of 35 depends as much on its motion through space as on its internal properties. For ultra-small galaxies, orbital history is a determining factor in whether they survive or dissolve. Gravity from a massive host galaxy can either gradually erode a satellite or leave it largely intact, depending on the details of its trajectory. 35's present structure reflects an orbital path that has avoided the most destructive outcomes. Satellite galaxies experience tidal forces as they orbit larger systems. These forces arise because gravity acts unevenly across an extended object. The side of a satellite closer to the host feels a stronger pull than the far side. If the difference exceeds the satellite's internal binding, stars and dark matter can be stripped away. Over time, repeated tidal encounters can reduce a galaxy to a diffuse remnant, or erase it entirely. XXXV shows little evidence of such extreme disruption. Its stellar distribution remains coherent, with no obvious tidal tails or pronounced elongation. This suggests that tidal stripping has been limited. Either the galaxy's orbit keeps it at relatively large distances from the Milky Way's centre, or its dark matter halo provides sufficient binding to resist disruption during closer passages. The shape and symmetry of 35 offer indirect clues about its past. Strong tidal interactions tend to distort satellites, producing asymmetric density profiles or extended stellar streams. These features are common among satellites that have undergone multiple close pericentric passages. 35's comparatively regular appearance indicates a more gentle interaction history. Timing of infall into the Milky Way system also matters. Satellites that joined early encountered a smaller host galaxy. While they experience environmental effects over longer periods, the tidal field was initially weaker. Satellites accreted later faced a more massive host, but over shorter timescales. 35's preserved structure is consistent with either scenario, but in both cases its orbit must have avoided repeated deep plunges into the inner halo. Orbital eccentricity plays a critical role. Highly eccentric orbits bring satellites close to the host at pericenter, where tidal forces peak. More circular orbits keep satellites at relatively constant distances, reducing tidal stress. Although precise orbital parameters for 35 are difficult to measure, its survival implies that extreme eccentricity is unlikely. Inclination relative to the Milky Way's disk also influences stability. Satellites that pass through or near the disk experience tidal shocks and interactions with dense gas. These encounters can rapidly heat and strip small systems. 35's lack of obvious disk-induced damage suggests that its orbit avoids frequent disk crossing. Dark matter retention is closely tied to orbital history. Tidal stripping typically removes outer dark matter first. As the halo shrinks, the remaining structure becomes more vulnerable. 35's continued dark matter dominance indicates that its core halo remains intact. This implies limited cumulative stripping over cosmic time. Interactions with other satellites are another potential threat. In regions with high satellite density, close encounters can alter orbits and enhance stripping. XXXV appears relatively isolated from major satellite groupings, reducing the likelihood of such interaction. This isolation contributes to its long-term stability. Over billions of years, even mild tidal forces can have cumulative effects. Gradual heating can expand stellar orbits and reduce central densities. The fact that 35 remains bound and identifiable indicates that these processes have operated slowly. Its evolution has been dominated by endurance rather than transformation. The survival of 35 highlights an important selection effect. The ultra-faint galaxies observed today are likely survivors of a larger initial population. Many similar systems may have formed but followed less favourable orbits, leading to their destruction. Observed systems therefore represent a biased sample shaped by environmental filtering. This bias affects how astronomers interpret the faint end of the galaxy population. The properties of surviving galaxies reflect not only formation physics but also survival probabilities. 35's characteristics may differ from those of destroyed systems, limiting how directly observations can be generalized. Orbital stability also influences internal evolution. Repeated tidal shocks can trigger star formation or structural changes. 35 shows no evidence of such events. Its star formation ended early and was not reignited by later interactions. This suggests a relatively quiescent orbital history after initial infall. The interplay between internal binding and external forces defines a narrow survival window. 35's dark matter halo provides resilience, while its orbit limits exposure to destructive environments. Both factors are necessary. A similar halo on a harsher orbit might not survive, and a gentler orbit without sufficient binding would still fail. Understanding 35's orbital history helps explain why ultra-small galaxies are rare. Formation alone does not guarantee survival. Long-term stability requires favourable dynamics. This adds a second layer of selection beyond star formation thresholds. XXXV, therefore, represents a successful outcome in a challenging regime. It navigated the Milky Way's gravitational environment without being torn apart. Its continued existence allows astronomers to study a system that retains information about early cosmic condition. By examining orbital history and stability, researchers gain insight into the processes that shape satellite populations. 35 demonstrates how motion through space influences which galaxies persist and which disappear. Its survival is not accidental, but the result of a specific balance between gravity, environment, and time. This balance leaves 35 as a long-lived witness to the early universe. Its orbit preserved it when many others were lost. In doing so, it provides a rare opportunity to study the smallest scales of galaxy formation and survival within a complex gravitational landscape. 35 and the threshold between galaxies and darkness. XXXV occupies a critical position in the hierarchy of cosmic structures. It exists at the boundary where galaxies cease to be reliably luminous, and dark matter halos transition into objects that leave no observable trace. This threshold is not defined by a single property such as mass or size, but by the interaction of multiple physical limits. 35 helps clarify where that boundary lies and why it matters. In cosmological terms, dark matter halos form across a wide range of masses. Simulations predict a smooth continuation of structure down to very small scales. What does not continue smoothly is the ability of those halos to host stars. Below a certain scale, star formation becomes increasingly rare and eventually absent. 35 lies just above that cutoff. This position explains both its existence and its rarity. 35 is massive enough to have briefly retained gas and formed stars, but only marginally so. Small variations in timing, environment, or feedback could have pushed it below the threshold entirely. In that case, it would exist today as a dark halo with no stars, indistinguishable from the background of dark matter substructure. The threshold nature of 35 challenges simplified definitions of galaxies. Traditional classifications rely on visible features: stars, brightness, structure. At this scale, those criteria become unreliable. A system with only a few thousand stars may still qualify as a galaxy if it is embedded in a dark matter halo. XXXV demonstrates that the defining feature of a galaxy at the smallest scales is not luminosity, but gravitational context. This distinction has implications for how the cosmic inventory is counted. Observational surveys detect only luminous objects. If most small halos never form stars, then the visible galaxy population represents only a fraction of existing structure. XXV provides evidence that this fraction extends lower than once believed, but still does not reach the full predicted population. The boundary also affects interpretations of reionization. Small galaxies are thought to have contributed to the ultraviolet radiation that reionized the universe. However, if star formation shuts down sharply below a certain scale, then the contribution of the smallest halos may be negligible. 35 suggests that only halos slightly above the threshold participated meaningfully in early star formation. This has consequences for models that rely on numerous faint galaxies to explain reionization. If systems like 35 are rare, then larger dwarf galaxies must carry more of the burden. The threshold, therefore, shapes not only the present-day galaxy population, but also the early thermal history of the universe. Feedback processes reinforce the boundary. Once star formation begins in a marginal halo, it generates forces that work against continued activity. Supernova explosions, stellar winds, and radiation heat, and expel gas. In a system barely capable of holding on to gas, these effects can be decisive. 35 likely crossed the threshold once, then fell back below it permanently. Environmental effects sharpen the cutoff further. As a satellite of the Milky Way, 35 was exposed to a hot halo and tidal forces. These external pressures reduce the margin for survival. A similar halo in isolation might have formed slightly more stars. Conversely, a halo slightly smaller than 35 would have failed entirely under the same conditions. The threshold is therefore not universal. It depends on redshift, environment, and radiation background. 35 formed stars when the universe was denser, and conditions briefly favoured cooling. The same halo forming later might never have done so. This time, dependence complicates efforts to define a single mass scale for galaxy formation. XXXV also informs the interpretation of ultrafaint galaxy statistics. Each discovery near this boundary carries disproportionate weight. Small changes in survey depth or sky coverage can reveal new systems or leave them hidden. This sensitivity reflects how sharply the luminous population declines near the threshold. The existence of 35 confirms that the boundary is not absolute. There is no hard line separating galaxies from non-galaxies. Instead, there is a transition zone where outcomes depend on chance and context. Some halos barely succeed, others barely fail. 35 belongs to the former category. Understanding this transition helps reconcile theory and observation. Simulations predict many small halos, while observations find few small galaxies. The threshold explains why both can be correct. Most halos exist, but only a minority cross the conditions required for star formation. 35 is a visible marker of that minority. This perspective also reframes the concept of smallest galaxy. 35 is not simply the smallest example of a continuous class. It represents the edge of a physical process. Beyond it, galaxies cease to form stars and become observationally invisible. By studying 35, astronomers gain insight into where and why the universe stops producing light at small scales. This boundary defines the limit of what can be observed directly and highlights how much of cosmic structure remains unseen. XXXV stands at this edge, illuminating the point where galaxies give way to darkness. Chemical evolution at the edge of galaxy formation. The chemical composition of 35 provides one of the clearest windows into its past. Unlike larger galaxies whose chemical histories are layered and complex, 35 exhibits a record that is brief, sparse, and incomplete. This simplicity is not a limitation. It is evidence of how chemical evolution behaves when star formation occurs at the very edge of viability. At this scale, enrichment does not proceed gradually. It happens in short, uneven bursts and then stops. Chemical evolution begins with the first generation of stars. In the early universe, gas clouds contained almost no heavy elements. Hydrogen and helium dominated, with trace amounts of lithium. When the first stars formed, they created heavier elements through nuclear fusion and dispersed them through stellar winds and supernova explosions. In large systems, this process repeats many times, steadily increasing metallicity. In 35, it appears to have occurred only briefly. Spectroscopic studies of 35 stars show extremely low metallicity. These stars contain only small amounts of elements heavier than helium, indicating that they formed from gas that had undergone minimal prior processing. This places their formation early in cosmic history, before enrichment became widespread. The metallicity levels observed are consistent with a system that experienced only a handful of enrichment events. The limited number of stars in 35 means that chemical signatures are not averaged over large populations. In massive galaxies, thousands of supernovae contribute to enrichment, smoothing out variations. In 35, individual supernovae likely had outsized influence. A single massive star exploding could significantly alter the chemical composition of the remaining gas. As a result, the chemical record may preserve the imprint of specific early stars rather than a blended history. Elemental abundance ratios provide further clues. Ratios between alpha elements and iron reflect the types of supernova that contributed to enrichment. In systems dominated by early massive stars, alpha elements tend to be enhanced relative to iron. This pattern is expected when enrichment is driven primarily by core collapse supernovae, which occur quickly after star formation begins. 35's available measurements are consistent with this scenario, supporting the idea of rapid early star formation followed by abrupt cessation. The absence of enrichment from longer-lived stellar processes is equally informative. Type ER supernovae, which contribute significant iron, occur on longer timescales. Their signatures are prominent in galaxies with extended star formation histories. In 35, there is little evidence for their influence. This suggests that star formation ended before these later processes could contribute meaningfully. Chemical dispersion within 35 also appears limited. Some ultra-faint galaxies show internal metallicity spreads, reflecting multiple star-forming episodes or incomplete mixing. XXXV's small stellar sample makes definitive conclusions difficult, but the overall consistency of low metallicity suggests minimal chemical evolution. Gas may have been expelled before thorough mixing occurred, freezing the chemical state of the system. This lack of mixing is expected in shallow gravitational potentials. In small halos, supernova-driven outflows can remove gas rapidly. Once gas escapes, there is no opportunity for subsequent stars to form from enriched material. The galaxy's chemical evolution effectively halts. 35 fits this pattern closely. The simplicity of 35's chemical record has broader implications. It provides a near-direct probe of early nucleosynthesis under conditions difficult to study elsewhere. The stars of 35 likely formed from gas enriched by some of the earliest supernovae in the universe. Their compositions can be compared with theoretical models of early stellar yields, offering constraints on the nature of the first generations of stars. This makes 35 valuable beyond galaxy formation studies. It contributes to understanding stellar evolution at low metallicity. Early stars may have differed significantly from later populations in mass, rotation, and explosion mechanisms. Systems like 35 preserve evidence of these differences. Chemical simplicity also affects how 35 is classified. Its low metallicity reinforces its distinction from star clusters. While clusters can be metal poor, their chemical homogeneity typically reflects formation from already enriched gas within larger galaxies. 35's chemistry suggests an independent enrichment history tied to its own brief star formation. The galaxy's chemical state also informs models of feedback. Even minimal star formation can produce enough energy to expel gas in small systems. 35's chemical record implies that feedback was effective early, removing gas before extensive enrichment could occur. This reinforces the idea that feedback thresholds play a decisive role at small scales. From a population perspective, 35 likely represents the upper edge of chemical viability among ultra-small galaxies. Systems slightly smaller may have formed stars too briefly to leave any detectable chemical signature. Others may have formed none at all. 35 occupies a narrow band where chemical evolution occurred just long enough to be observed. This perspective helps explain why ultra-faint galaxies show such uniformly low metallicities. They are not simply inefficient versions of larger galaxies. They are fundamentally different in how chemical processes unfold. Their histories are truncated, not prolonged. The chemical evolution of 35 therefore reflects a balance between formation and loss. It formed stars early enough to initiate enrichment, but lost gas too quickly to sustain it. This balance defines the chemical endpoint of galaxy formation at the smaller scales. Understanding this endpoint refines broader models of chemical evolution in the universe. It shows that chemical complexity is not inevitable. Under certain conditions, enrichment stops almost as soon as it begins. These conditions were common in the early universe and persist today in relic systems like 35. XXXV's chemistry is thus a fossil record of both success and failure. It records the moment when star formation briefly succeeded and the conditions that caused it to end. This record has remained largely unchanged for billions of years, preserved by the galaxy's isolation and small size. By studying chemical evolution in 35, astronomers gain insight into the earlier stages of galaxy formation and the limits imposed by physics. Its simplicity is not an absence of information, but a concentrated signal from a time when the universe was young and the rules of structure formation were still being established. In this way, 35 demonstrates that chemical evolution is not merely a byproduct of star formation. It is a diagnostic of how close a system came to the edge of viability. 35 crossed that edge briefly, left its chemical mark, and then retreated into silence. Structural simplicity and the absence of internal evolution. The present-day structure of 35 reflects a system that has undergone remarkably little internal change since its formation. Unlike larger galaxies, where structure evolves through sustained star formation, mergers, and dynamical reshaping, 35 shows few signs of such processes. Its simplicity is not accidental. It is the outcome of limited internal drivers and early isolation from transformative events. Galactic structure is shaped by repeated interactions between stars, gas, and dark matter. In massive galaxies, these interactions are continuous. Gas inflows deepen central potentials. Star formation builds disks or spheroids, and feedback redistributes mass. Over time, these processes generate complex morphologies. XXXV lacks nearly all of these mechanisms. Its evolution has been dominated by what did not happen, rather than what did. From the outset, 35 formed with a very small stellar population. This limited its ability to drive internal change. Stellar interactions depend on density. In dense systems, gravitational encounters transfer energy, leading to mass segregation and structural evolution. In 35, stellar densities are extremely low. The timescale for significant two-body interactions exceeds the age of the universe. As a result, its stars largely preserve their original orbital configurations. The absence of gas after early times further reduced internal evolution. Gas is a primary agent of change in galaxies. It cools, collapses, forms stars, and responds to gravitational perturbations. Without gas, 35 became dynamically inert. No new stars formed to alter mass distribution, and no dissipative processes remain to reshape structure. This inertness is reflected in the galaxy's morphology. 35 appears diffuse, with a smooth decline in stellar density and no evidence of internal substructure such as bars, disks, or cores shaped by baryonic processes. Its appearance is consistent with a system whose structure was set early and then preserved. Dark matter dominates this structure. The gravitational potential is defined almost entirely by the dark matter halo. Stars act as test particles, tracing the potential rather than shaping it. This contrasts with larger galaxies, where baryonic matter can significantly modify the dark matter distribution through processes such as adiabatic contraction or feedback-driven expansion. Because baryonic influence is minimal, 35 provides a near-direct view of dark matter-dominated structure. Its stellar distribution likely follows the underlying halo shape closely. This makes it useful for studying how dark matter halos behave when baryonic complications are absent or negligible. The lack of internal evolution also means that 35 did not experience secular processes common in larger galaxies. There is no evidence of internal angular momentum redistribution, disk thickening, or central mass buildup. These processes require sustained star formation or gas inflow, both of which were absent after early times. Structural stability over long periods also implies that 35 avoided mergers. Even minor mergers can significantly alter small systems, adding stars, heating orbits, and changing shape. The absence of such signatures suggests that 35 formed in relative isolation and remain so. This isolation is consistent with its low mass and peripheral location. The simplicity of 35's structure helps distinguish it from disrupted remnants. Some ultra-faint systems may represent the remains of once larger galaxies stripped down by tidal forces. Such remnants often show irregular shapes, gradients, or signs of past complexity. 35 does not. Its simplicity appears primordial rather than the result of erosion. This distinction matters for interpreting faint galaxies. Not all small systems share the same origin. Some are survivors of larger progenitors, while others formed small and stayed small. XXXV belongs to the latter category. Its structure supports a formation scenario where limited growth occurred from the beginning. The lack of internal evolution also affects stellar populations. In galaxies with prolonged activity, stellar orbits are continually altered by changing potentials. In 35, stellar orbits have remained largely unchanged since formation. This preserves kinematic information about early conditions that would otherwise be erased. From a theoretical perspective, 35 represents a baseline case. It approximates the outcome of galaxy formation in the absence of sustained baryonic processes. Comparing such systems with more complex dwarfs helps isolate the effects of feedback, gas dynamics, and star formation on structure. This baseline is valuable for testing simulations. Many models struggle to reproduce the correct structures of dwarf galaxies, often producing too much central concentration or too much disruption. 35's simplicity provides a clear target. Any successful model must be able to produce systems that form early, stop evolving internally, and remain structurally stable for billions of years. The absence of internal evolution also influences how 35 responds to external forces. A dynamically cold, dark matter-dominated system reacts differently to tides than a baryon-rich one. Its response is smoother and less chaotic. This may contribute to its survival, as there are fewer internal resonances to amplify external perturbations. Over cosmic time, 35 has therefore remained close to its initial state. Its structure today is a preserved outcome of early conditions, rather than the product of continuous reshaping. This makes it an unusually clean object for studying the earliest phases of galaxy formation. The simplicity observed in 35 is not common among galaxies, but it may have been common in the early universe. Many small systems likely formed briefly and then froze in place. Most have since been destroyed or rendered invisible. 35 remains as one of the few accessible examples. By examining structural simplicity and the absence of internal evolution, astronomers gain insight into a regime of galaxy formation that is otherwise inaccessible. XXXV shows what happens when growth stops almost as soon as it begins. It preserves a structure defined by dark matter and early star formation, unchanged by later complexity. This preservation is not a limitation of the system, but its defining characteristic. It allows 35 to function as a reference point for understanding how galaxies behave when the usual drivers of evolution are absent. In doing so, it clarifies the role those drivers play in shaping the more familiar galaxies that dominate the observable universe. 35 as a test of galaxy formation models. The existence of 35 presents a direct challenge to theoretical models of galaxy formation. While large galaxies offer many observable features, they are shaped by numerous overlapping processes that complicate interpretation. XXXV strips this complexity away. Its small size, early formation, and limited evolution make it a stringent test case. Any successful model of galaxy formation must be able to explain not only how large galaxies form, but how systems like 35 come into existence and persist. Most modern galaxy formation models are built on a hierarchical framework. In this picture, dark matter halos form first, merge over time, and provide gravitational wells into which gas falls and forms stars. This framework works well at large scales. However, as halo mass decreases, predictions become more uncertain. Models must account for why some small halos host stars, while many others do not. 35 lies precisely at this uncertain boundary. One difficulty arises from star formation thresholds. Many simulations impose minimum halo masses or gas densities below which star formation is suppressed. These thresholds are often calibrated to match observations of brighter galaxies. Systems like 35 test whether those thresholds are too strict. Its existence implies that star formation can occur in halos smaller than some models allow, at least under early universe conditions. Timing plays a critical role. In simulations, the epoch at which a halo forms can determine whether it ever becomes luminous. Halos that collapse early, before reionization, have a greater chance of retaining cold gas and forming stars. Halos that collapse later often remain dark. 35's old stellar population supports this timing-dependent picture. Models must therefore accurately capture early collapse histories to reproduce systems like it. Feedback implementation is another challenge. Stellar feedback is necessary to prevent overproduction of stars in small galaxies, but too much feedback can erase star formation entirely. XXXV suggests that feedback operated strongly enough to shut down star formation early, but not so strongly as to prevent it altogether. This balance is difficult to achieve in simulations, where feedback prescriptions are often simplified. Chemical evolution adds further constraints. 35's low metallicity and limited enrichment require models to reproduce brief, inefficient star formation followed by early gas loss. Continuous or extended star formation histories would over-enrich the system. Models must therefore allow for rapid truncation without invoking extreme or finely tuned parameters. Dark matter physics also enters the picture. Standard cold dark matter models predict abundant small halos, but must explain why only a fraction become luminous. Alternative models, such as warm or self-interacting dark matter, modify small-scale structure. 35 provides a lower bound on halo mass capable of hosting stars. Any dark matter model that suppresses halos below this scale would struggle to explain its existence. Internal structure predictions are equally important. Some simulations produce overly dense central regions or overly diffuse systems at small scales. XXXV's structural simplicity and stability require models to generate halos that can remain bound without significant reshaping. This places constraints on both initial conditions and subsequent evolution. Environmental effects must also be captured accurately. 35 did not evolve in isolation. As a satellite of the Milky Way, it experienced tidal forces and gas stripping. Models that ignore environmental interactions may misrepresent survival probabilities. Conversely, models that overestimate environmental destruction may predict too few survivors, like 35. Resolution limits in simulations complicate matters further. Ultra-small galaxies require extremely high resolution to model accurately. Many simulations simply cannot resolve systems at this scale in detail. As a result, predictions for objects like 35 often rely on extrapolation rather than direct modelling. Observations therefore play a critical role in guiding and validating these extrapolations. XXXV also highlights stochasticity in galaxy formation. At small scales, outcomes depend on chance events, the timing of the first stars, the location of supernova, the local radiation field. Two halos of similar mass may follow entirely different paths. One may form stars briefly, like 35, while another remains dark. Models must incorporate this randomness rather than relying solely on deterministic thresholds. This stochasticity complicates comparisons between theory and observation. The presence of a single system, like 35, does not invalidate a model, but its absence in simulations could indicate missing physics. Conversely, overproduction of similar systems could suggest feedback or suppression mechanisms are too weak. XXXV therefore serves as a calibration point. It defines what is possible rather than what is typical. Models that reproduce galaxies like XXXV demonstrate flexibility and realism. Those that cannot must be revised. The importance of 35 extends beyond matching a single object. It influences predictions for the population of faint galaxies as a whole. If models allow too many 35-like systems, they may conflict with observations. If they allow too few, they may underestimate star formation in small halos. The correct balance is narrow. XXXV also informs how observational surveys are interpreted. The detection of such faint systems depends on survey depth, sky coverage, and analysis methods. Models must be compared with observations in a consistent way, accounting for selection effects. 35's discovery suggests that some predicted systems may exist, but remain undetected. In this sense, 35 bridges theory and observation. It forces models to confront real data at the smaller scales. It also encourages observers to refine search strategies based on theoretical expectations. Ultimately, 35 underscores that galaxy formation is not a one-size-fits-all process. At small scales, simple scaling relations break down. New physical regimes emerge where timing, environment, and feedback dominate outcomes. Models that succeed at large scales must still pass through this narrow regime. XXXV stands as a benchmark for that test. It represents the smallest systems that still qualify as galaxies. Explaining how it formed, evolved, and survived is not a peripheral exercise. It is central to validating the foundations of galaxy formation theory. By confronting models with the reality of 35, astronomers gain a clearer picture of where current understanding succeeds and where it falls short. This process drives refinement, not only of simulations, but of the physical assumptions that underlie them. 35 thus plays a role disproportionate to its size, shaping how galaxies are understood across the universe. 35 in the context of the local group. To understand 35 fully, it must be placed within the broader environment in which it exists. 35 is not an isolated curiosity, but part of the local group, a collection of galaxies dominated by the Milky Way and Andromeda. The properties of 35 reflect both its intrinsic formation history and the influence of this shared environment. Examining 35 alongside other local group systems clarifies what makes it typical, what makes it rare, and what it reveals about galaxy populations at the smallest scales. The local group contains dozens of known dwarf galaxies spanning a wide range of masses, luminosities, and star formation histories. At the high end are systems like the Magellanic Clouds, which remain gas-rich and actively form stars. At the low end are ultra-faint dwarfs like 35, with minimal stellar content and no ongoing star formation. This diversity illustrates how galaxy evolution diverges sharply at small masses. XXXV occupies the extreme faint end of this spectrum. Its stellar mass is orders of magnitude lower than that of classical dwarf spheroidals such as Fornax or Sculptor. Yet it shares key characteristics with them, including dark matter dominance, old stellar populations, and lack of gas. This continuity suggests that ultra-faint dwarfs are not a separate class, but the low-mass extension of a broader dwarf galaxy population. Comparisons with other ultra-faint dwarfs reveal common patterns. Most are chemically primitive, dominated by ancient stars, and strongly dark matter dominated. These similarities point to shared formation conditions, many likely formed before or during cosmic reionization and lost their gas early. XXXV fits squarely within this pattern, reinforcing the idea that early universe processes shaped the smallest galaxies. At the same time, 35 shows differences that matter. Its structural regularity and apparent lack of tidal disturbance distinguish it from some ultra-faint dwarfs that appear partially disrupted. This suggests variation in orbital histories within the local group. While many small galaxies were heavily affected by interactions with the Milky Way, 35 seems to have followed a relatively benign path. The local group environment imposes constraints that differ from those in more isolated regions. Satellites experience tidal forces, ram pressure stripping, and interactions with the host halo. These effects preferentially remove gas and truncate star formation in small systems. 35's properties are consistent with this environmental processing, but also indicate that environment alone does not determine outcome. Internal thresholds and early timing remain decisive. The spatial distribution of ultra-faint dwarfs in the local group also provides context. Many are clustered near the Milky Way, reflecting both observational bias and true physical association. Systems farther away are harder to detect and may be underrepresented. 35's discovery implies that additional faint systems may exist at larger distances, hidden by current detection limits. Comparisons with Andromeda's satellite population strengthen this interpretation. Surveys around Andromeda have revealed a similarly rich population of faint dwarfs, some with properties closely resembling those of Milky Way satellites. This parallel suggests that the processes shaping 35 are not unique to one host galaxy. They reflect more general mechanisms operating across the local group. XXXV also informs discussions about satellite anisotropy and planar distributions. Some satellite galaxies appear aligned in thin planes around their hosts, raising questions about their origins. Whether 35 participates in such structures is uncertain, but its inclusion in broader analyses helps test whether ultra-faint dwarfs follow the same spatial patterns as brighter satellites. The local group context also matters for interpreting survival rates. Many small galaxies likely formed but did not survive to the present day. Tidal destruction, mergers, and complete stripping reduced their numbers. The galaxies observed today, including 35, represent a filtered population. Their properties reflect both formation physics and survival bias imposed by the local group environment. XXXV's role in this filtered population is instructive. Its survival suggests that even extremely small galaxies can persist if conditions align. This challenges earlier assumptions that ultra-small systems would inevitably be destroyed. Instead, survival appears probabilistic rather than guaranteed or impossible. The local group also provides a laboratory for testing cosmological models. Because distances and stellar populations can be studied in detail, small discrepancies become apparent. 35 contributes to these tests by anchoring the faint end of the galaxy distribution. Its properties help define what models must reproduce at the smallest scales. In addition, 35 influences estimates of the total mass of the Milky Way halo. Satellite dynamics provide constraints on the host's gravitational potential. Each satellite adds information, particularly when it occupies a unique region of parameter space. While 35 alone has limited impact, collectively ultra-faint dwarfs refine mass estimates and halo models. The local group context also shapes future discovery strategies. Knowing that systems like 35 exist encourages deeper, wider surveys designed to uncover similar objects. The local group remains incomplete at the faint end, and 35 serves as evidence that further discoveries are likely. 35's integration into the local group narrative highlights a broader theme. The smallest galaxies are not outliers, but integral components of galactic ecosystems. They interact with their hosts, respond to shared cosmic events, and preserve early histories that larger systems obscure. In this sense, 35 acts as both participant and witness. It participated in the early assembly of the local group and has witnessed its evolution largely unchanged. Its presence enriches understanding of how the local group formed and how its smallest members endured. By examining 35 within the local group, astronomers move beyond isolated case studies. They place small galaxies into a coherent framework that links formation, environment, and survival. Demonstrates how much information can be extracted from even the faintest members of a galactic family. This contextual view reinforces the scientific value of 35. It is not merely the smallest known galaxy, but a key reference point within a well-studied cosmic neighborhood. Through it, the local group reveals not only its largest structures, but its most delicate ones as well. Detection limits and Y system like 35 are rarely seen. The discovery of 35 raises an immediate question. If such galaxies exist, why are so few of them known? The answer lies not in their rarity alone, but in the severe limits imposed by observation. Ultra-small galaxies challenge the capabilities of modern astronomy, sitting at the edge of what current instruments and surveys can detect. Understanding these limits is essential for interpreting how representative 35 truly is. The primary obstacle is luminosity. 35 contains only a small number of stars, most of them old and faint. Its total brightness is extremely low, spread over a relatively large area of sky. This combination produces very low surface brightness, making the galaxy difficult to distinguish from background noise. Traditional surveys designed to detect brighter and denser systems are poorly suited to identifying objects like 35. Distance compounds the problem. Even within the local group, small increases in distance can render ultra-faint galaxies invisible. A system like 35, placed just a few 100,000 light-years farther away, could easily fall below detection thresholds. This creates a strong bias toward discovering only the nearest examples, distorting perceptions of how common such galaxies are. Foreground contamination further complicates detection. The Milky Way contains vast numbers of stars that overlap the sky positions of distant systems. Separating the sparse stellar population of 35 from foreground stars requires precise photometry and careful statistical analysis. Without deep imaging and sophisticated filtering, the galaxy's stars blend into the background. Survey strategy also matters. Many wide-field surveys trade depth for coverage, missing the faintest systems. Others focus on specific regions of the sky, leaving large areas unexplored at sufficient depth. XXXV was identified through targeted analysis that combined deep imaging with refined selection techniques. Similar systems may remain undetected simply because they lie outside surveyed regions. Time investment is another limiting factor. Confirming a system like 35 requires follow-up observations, including spectroscopy to measure stellar velocities and chemical properties. These observations are time-consuming and resource-intensive. As a result, only a fraction of candidate systems can be studied in detail. Many potential ultra-faint galaxies remain unconfirmed. Detection is also influenced by assumptions built into search algorithms. Automated pipelines are often optimized to find objects with specific properties, such as compactness or particular color ranges. Systems that deviate from these expectations may be overlooked. 35's diffuse structure and minimal stellar population push against these assumptions. The role of dark matter adds an additional layer of invisibility. Dark matter dominates 35's mass, but contributes nothing to its light. This means that the galaxy's most important component is observationally silent. Only the stars reveal its presence, and they do so weakly. Any galaxy with even fewer stars would be effectively invisible, regardless of its dark matter content. This leads to a broader realization. The census of galaxies is fundamentally incomplete at small scales. Observations capture only those halos that form stars and did so efficiently enough to leave a detectable trace. Systems like 35 represent the extreme lower edge of this visible population. Below them lies a vast population of dark halos that remain unseen. Even within the luminous population, selection effects shape what is found. Galaxies with slightly higher stellar densities or favorable orientations are easier to detect. Those with similar total luminosity but more diffuse distributions may be missed. 35's detection does not imply that it is typical, only that it crossed observational thresholds. Future surveys promise improvement, but limitations will remain. Deeper imaging will reveal fainter systems, but confusion with background sources will persist. Spectroscopic follow-up will continue to be a bottleneck. Even with next-generation telescopes, the smallest galaxies will challenge detection. Understanding these limits helps avoid misinterpretation. The apparent scarcity of 35-like galaxies does not necessarily reflect true scarcity. It reflects the difficulty of seeing them. This distinction is critical when comparing observations to theoretical predictions. Simulations predict many small halos, but only a subset become visible galaxies. Observations detect only a subset of those visible galaxies. Each step introduces bias. 35 occupies the narrow overlap between what exists and what can be seen. Its discovery suggests that this overlap extends lower than previously confirmed, but not necessarily to the full extent predicted by theory. Detection limits also influence how galaxy properties are inferred statistically. If the faintest systems are underrepresented, average properties may be skewed. Ultra-faint galaxies, like 35, could differ systematically from slightly brighter dwarfs, but their influence on population averages is muted by small numbers. This has implications for understanding dark matter and galaxy formation. Constraints derived from observed populations must account for what is missing. Systems, like 35, help anchor the lower end of what is observable, providing a reference point for correcting biases. The challenge of detection also explains why discoveries of ultra-small galaxies often occur in bursts. Improvements in data processing, survey depth, or analysis techniques suddenly reveal multiple new systems. These discoveries reflect changes in capability rather than sudden changes in the universe. XXXV's detection underscores the importance of methodology. It was not found because it was intrinsically prominent, but because techniques were refined to extract weak signals from noise. This suggests that further progress depends as much on analysis as on instrumentation. The rarity of known systems like 35 should therefore be interpreted cautiously. They are rare in catalogues, not necessarily in reality. Their invisibility is a product of physical faintness and observational constraint. By recognizing these limits, astronomers can better frame the significance of 35. It is not a lone outlier, but a representative of a population that remains largely hidden. Its discovery reveals how much of the universe's small-scale structure lies beyond current visibility. This realization shifts the focus from counting galaxies to understanding thresholds. It is less important to know exactly how many 35-like systems exist than to understand why they are so hard to see. That understanding informs both theoretical models and observational strategies. XXXV stands at the edge of detection, marking the boundary between what astronomy can currently observe and what it infers indirectly. Studying this boundary clarifies the limits of knowledge and highlights where future discoveries are most likely to occur. Implications for the dark matter census of the universe. The existence of 35 has consequences that extend well beyond the study of dwarf galaxies. At its core, 35 reshapes how astronomers think about the total inventory of dark matter in the universe. While dark matter is usually discussed in terms of large-scale structure and galaxy clusters, systems like 35 show that its most revealing behavior may occur at the smaller scales. Dark matter halos form across a vast range of masses. Cosmological simulations predict a steep rise in the number of halos as mass decreases. In other words, small halos should be far more numerous than large ones. However, the majority of these halos are invisible because they contain few or no stars. XXXV sits at the threshold where a halo barely managed to produce a detectable stellar population. This makes it a critical data point in estimating how many dark halos exist beyond current observational reach. If galaxies like 35 are representative of the faintest luminous systems, then they define the lower bound of the visible dark matter census. Below this bound lies a potentially enormous population of starless halos. These halos would contribute mass to the universe without contributing light. Understanding where this boundary lies affects estimates of how dark matter is distributed on small scales. The mass-to-light ratio of 35 illustrates this imbalance directly. Its stars account for only a tiny fraction of its total mass. The overwhelming majority is dark matter. This ratio increases dramatically as galaxy luminosity decreases. In large galaxies, Dark matter dominates outer regions, but baryons play a significant role in the center. In 35, baryons are negligible everywhere. The galaxy is effectively a dark matter object with a minimal luminous tracer. This has implications for how dark matter is mapped. Many techniques rely on luminous matter to trace gravitational potentials. Rotation curves, stellar motions, and gas dynamics all depend on visible components. In systems like 35, the visible traces are sparse and noisy. This limits precision, but also emphasizes how much mass can exist with almost no light. The dark matter census is therefore incomplete in two ways. First, many halos are completely dark. Second, even luminous halos like 35 reveal only a small fraction of their mass through stars. This means that observational inventories systematically undercount dark matter structures at small scales. XXXV also informs how dark matter halos populate the local group. If one such system exists and is detectable, it implies that many similar halos likely exist but remain unseen. These halos contribute to the total mass of the Milky Way's environment. Their gravitational influence may affect satellite dynamics, tidal streams, and the overall structure of the halo, even if they are not individually observable. This realization complicates efforts to reconcile observations with simulations. Simulations predict many subhalos. Observations find few satellites. XXXV demonstrates that at least some predicted halos do host stars, but only marginally. The gap between predicted halos and observed galaxies may therefore reflect a steep drop in star formation efficiency rather than an absence of structure. This distinction matters for dark matter theory. Some alternative dark matter models attempt to reduce the number of small halos to match observed satellite counts. If many halos exist but remain dark, then reducing halo abundance may not be necessary. Instead, the focus shifts to understanding why most halos fail to form stars. XXXV supports this interpretation by showing that the transition from luminous to dark occurs at very small scales. The internal structure of 35's dark matter halo also affects the census. If its halo is centrally concentrated, it may be more resistant to tidal destruction. This would increase the survival rate of small halos. If halos are more diffuse, destruction rates would be higher, reducing the present-day population. 35's survival suggests that at least some small halos are robust over cosmic time. The cumulative mass of small halos is another consideration. Individually, systems like 35 contain little mass compared to large galaxies. Collectively, however, they could represent a non-negligible fraction of dark matter in galaxy halos. Even if most remain starless, their gravitational effects add up. This cumulative contribution is difficult to measure directly. It must be inferred from simulations and indirect observational constraints. XXXV provides an anchor point for these inferences. It marks a scale where dark matter halos are confirmed to exist and persist. Extrapolating below this scale requires assumptions, but those assumptions are now better informed. The dark matter census also influences interpretations of cosmological observations beyond the local group. Small halos affect gravitational lensing, the distribution of matter in cosmic filaments, and the smoothness of dark matter on small scales. Constraints from these observations depend on how much mass resides in small halos versus larger ones. 35 helps constrain that distribution. There is also a feedback loop between baryons and the dark matter census. If star formation is extremely inefficient at small scales, then baryonic physics determines which halos become visible. This selection effect means that the luminous galaxy population does not trace the dark matter population uniformly. Systems like 35 highlight how misleading it can be to equate galaxies with halos. In this context, 35 is more than a curiosity. It is a calibration point. It shows that halos near the minimum mass for star formation can survive and be detected under favourable conditions. This constrains how sharply the luminous fraction drops with decreasing halo mass. Future surveys will refine this picture, but 35 already shifts expectations. It suggests that the dark matter census includes a vast unseen component at small scales. The visible universe captures only the brightest peaks of a much larger structure. This perspective reframes the relationship between galaxies and dark matter. Galaxies are not a complete map of matter distribution. They are biased traces, especially at the faint end. XXXV illustrates this bias clearly. Its dark matter outweighs its stars by orders of magnitude, yet without those stars, the galaxy would be invisible. Understanding this bias is essential for interpreting observations across cosmology. Whether studying galaxy clustering, halo mass functions, or the growth of structure, astronomers must account for what cannot be seen. Systems like 35 provide rare opportunities to probe this hidden regime directly. The implications extend to how future discoveries are valued. Each new ultra-small galaxy constrains the dark matter census more tightly. They define where visibility ends and inference begins. XXXV stands at this boundary, linking observable galaxies to the vast population of unseen halos. In doing so, it reshapes how astronomers think about the universe's mass budget. Dark matter is not just dominant in large structures, it dominates most completely in the smallest ones. 35 makes this dominance explicit and measurable. The dark matter census, once framed mainly in terms of large galaxies and clusters, increasingly depends on understanding objects like 35. These systems show where matter hides when light fades. They remind us that most of the universe's structure exists beyond direct observation, and that even the smallest visible galaxies carry information about an enormous unseen population. XXXV therefore plays a critical role in bridging observation and theory. It anchors estimates of dark matter abundance at the smallest scales where galaxies still form. Beyond it lies darkness, structured but unseen, shaping the universe in ways that astronomy is only beginning to infer. What 35 tells us about the first galaxies. XXXV offers a rare opportunity to examine galaxy formation as it likely occurred in the earliest phases of cosmic history. While most galaxies have undergone billions of years of growth, interaction and restructuring, XXXV appears to preserve conditions that were common when the universe was young. In this sense, it functions as a proxy for the first generation of galaxies, allowing astronomers to test ideas about how the earliest structures formed and evolved. The first galaxies emerged in a universe very different from the one observed today. Gas was hotter, metal poor, and exposed to rapidly changing radiation fields. Dark matter halos were smaller and more numerous. Under these conditions, galaxy formation was not a smooth or guaranteed process. Many halos likely failed to form stars altogether. Others formed stars briefly and then faded. 35 appears to belong to this latter category. Its stellar population indicates formation at very high redshift. The stars are old, with ages consistent with formation within the first few billion years after the Big Bang. Their low metallicity supports this timing, reflecting a universe that had not yet been significantly enriched by multiple generations of stellar activity. These properties align closely with expectations for early galaxies. One defining feature of the first galaxies is inefficiency. Star formation was sporadic and fragile. Cooling pathways were limited, and feedback effects were disproportionately strong. XXXV reflects this inefficiency clearly. Only a small fraction of its available gas was converted into stars. This suggests that early galaxies may have been far less luminous than once assumed, contributing light briefly and unevenly. This has important implications for how early cosmic light is interpreted. Models of the early universe often rely on large numbers of faint galaxies to explain phenomena such as reionization. If systems like 35 were common, then early star formation may have been dominated by short-lived, low-efficiency episodes rather than sustained activity. This would change estimates of how and when the universe became reionized. XXXV also sheds light on the structure of early galaxies. The absence of internal complexity suggests that the first galaxies were structurally simple. They lacked disks, bulges, or organized rotation. Instead, they were likely pressure-supported systems dominated by dark matter. This simplicity matches theoretical predictions for the earliest bound structures. The role of dark matter in early galaxies is also clarified by 35. In small systems, dark matter dictated structure almost entirely. Baryonic matter followed the gravitational potential rather than reshaping it. This contrasts with later stages of galaxy evolution, where baryons play a more active role in modifying dark matter distributions. 35 preserves the earlier regime, where dark matter was the primary architect. The chemical record in 35 further reinforces its connection to the first galaxies. Its stars likely formed from gas enriched by only a few supernovae. This suggests that early galaxies experience minimal chemical evolution before feedback shut down further star formation. Such systems would contribute to early metal enrichment locally, but would not sustain ongoing enrichment cycles. This localized enrichment pattern affects how early intergalactic medium enrichment is modeled. Rather than being driven by many moderately sized galaxies, enrichment may have been patchy, with small systems contributing briefly before becoming inactive. XXXV exemplifies how such contributions could occur without producing long-lived luminous galaxies. XXXV also informs the expected diversity among first galaxies. Not all early galaxies would have followed identical paths. Some would have grown into larger systems through mergers and continued accretion. Others, like 35, remained small and isolated. The early universe likely contained a wide spectrum of outcomes, shaped by timing, environment, and chance. This diversity complicates attempts to generalize from observations of bright, high-redshift galaxies. Observations naturally favor luminous systems with sustained star formation. These systems may not be representative of the majority of early galaxies. 35 provides a counterexample, highlighting how many early systems may have been faint, short-lived, and structurally simple. The survival of 35 to the present day adds another layer of insight. Many first galaxies likely did not survive intact. Mergers, tidal disruption, and accretion erased their identities. 35's survival implies that some early galaxies avoided these fates, preserving a direct link to the past. Its existence suggests that remnants of the first galaxies may still be accessible for study within the local group. This has implications for interpreting fossil records in other galaxies. Larger systems may contain stars that originated in early galaxies like 35, but were later accreted. These stars populate stellar halos and streams. Studying 35 helps identify the properties such stars would have had at formation, aiding efforts to reconstruct galactic assembly histories. XXXV also informs numerical simulations of the first galaxies. Simulating early galaxy formation is challenging due to the wide range of scales involved and the complexity of feedback processes. Systems like 35 provide concrete benchmarks. Simulations that fail to produce such systems may be missing key physics related to cooling, feedback, or dark matter behavior. Conversely, simulations that produce too many 35-like systems may overestimate star formation efficiency in small halos. The narrow window in which 35 formed stars suggest that successful early galaxies were the exception rather than the rule. Accurate modelling must reproduce both the existence and rarity of such systems. XXXV also helps clarify the transition from first galaxies to more complex systems. It represents a stopping point along that transition. While some early galaxies grew and evolved, others stalled. Understanding why 35 stalled sheds light on the conditions required for continued growth. Factors such as halo mass, gas accretion rate, and environment emerge as critical determinants. The connection between 35 and the first galaxies also emphasizes the importance of local observations for cosmology. While distant observations probe the early universe directly, they are limited by resolution and sensitivity. Nearby relics like 35 provide complementary information, allowing detailed study of early conditions at a level impossible for high redshift galaxies. This complementary approach strengthens confidence in theoretical interpretations. When properties inferred from distant observations align with those measured in local relics, models gain credibility. 35 thus plays a bridging role, connecting the observable present to the inferred past. The study of 35 also raises questions about how many such relics remain undiscovered. If similar systems exist elsewhere in the local group or beyond, they may offer additional windows into early galaxy formation. Their discovery would refine understanding of the first galaxy's diversity and prevalence. XXXV's relevance to early galaxy studies is therefore profound. It provides empirical evidence that some of the first galaxies were small, inefficient, and short-lived. It shows that early galaxy formation did not necessarily lead to growth and complexity. In many cases, it led to stagnation and preservation. This perspective reshapes narratives of cosmic history. The early universe was not populated solely by rapidly growing galaxies on the path to modern spirals and ellipticals. It also contained many systems that formed briefly and then froze in place. 35 stands as a surviving example of that path. By examining 35, astronomers gain insight into what the first galaxies were like in practice, not just in theory. Its properties ground abstract models in observable reality. They show that early galaxy formation was constrained, inefficient, and diverse. XXXV therefore acts as a living fossil of the first galaxies. Its stars, structure, and dark matter halo preserve conditions from a formative era. Studying it deepens understanding of how the universe's earlier structures formed, and why so many of them left only faint traces behind. In this way, 35 contributes to a more complete picture of cosmic origins. It reminds us that the universe's earliest chapters were written not only by the brightest objects, but also by the smallest ones. 35 and the nature of galactic failure. XXXV is often described in terms of what it is: small, faint, dark matter dominated, and ancient. Equally important, however, is what it represents in terms of what did not happen. XXXV is a record of galactic failure. Not failure in an absolute sense, but failure to grow, to sustain star formation, and to evolve into a more complex system. Understanding this kind of failure is essential to understanding galaxy formation as a whole, because success is only meaningful when contrasted with the many pathways that do not lead to large, luminous galaxies. Galaxy formation models often focus on growth. Halos merge, gas accretes, stars form, and structures become increasingly complex. This narrative fits massive galaxies well, but it does not describe the majority of dark matter halos that formed in the early universe. Most halos never became large galaxies. Many never formed stars at all. 35 occupies an intermediate position. It formed stars briefly, but then failed to continue along the growth trajectory. This form of failure is not random. It arises from identifiable physical constraints. The most immediate constraint is gravitational depth. XXXV's dark matter halo was deep enough to briefly retain gas, but not deep enough to protect it indefinitely. Once heating mechanisms intensified, either internally or externally, gas was lost. Without gas, growth stopped. This loss of gas is irreversible at small scales. Larger galaxies can replenish gas through accretion from the intergalactic medium or through mergers. XXXV could not. Its environment did not supply cold gas, and its shallow potential prevented capture of new material. Once the initial reservoir was removed, the galaxy became inert. Feedback played a decisive role in this process. Even limited star formation produces massive stars that end their lives violently. In a system like 35, a small number of supernovae can inject enough energy to expel most of the remaining gas. This feedback does not need to be prolonged. A brief episode is sufficient to shut down star formation permanently. Importantly, this shutdown does not require extreme conditions. 35 does not show evidence of unusually energetic feedback or rare events. Its evolution likely followed a typical path for halos near the minimum mass threshold for star formation. This suggests that galactic failure at small scales is common rather than exceptional. Reionization further reinforced this outcome. As the universe became ionized, gas heating increased everywhere. Halos like 35 were especially vulnerable. Even if some gas survived early feedback, reionization likely prevented it from cooling and collapsing again. This combination of internal and external suppression sealed the galaxy's fate. From this perspective, 35 represents a system that crossed the star formation threshold once and then fell back below it. This crossing was temporary. Timing mattered. Had 35 formed slightly earlier, it might have formed more stars before reionization. Had it formed slightly later, it might not have formed any at all. Its existence reflects a narrow window of opportunity. This narrow window highlights the stochastic nature of galaxy formation at small scales. Two halos with similar masses can experience very different outcomes depending on subtle differences in timing, environment, and internal processes. One may grow into a recognizable dwarf galaxy. Another may remain dark. 35 illustrates a marginal success that quickly turned into long-term stagnation. The concept of galactic failure also reframes how success is defined. From a cosmological perspective, 35 is not a failed galaxy. It achieved stability and survived for billions of years. What it failed to do was to accumulate mass and complexity. Its evolutionary path ended early, but it did not end catastrophically. This distinction matters when interpreting observations. Systems like 35 are often described as relics or fossils, implying passive preservation. In reality, they are products of active suppression. Their simplicity is the result of processes that halted growth, not merely the absence of later events. Understanding these suppression mechanisms helps explain why the galaxy population looks the way it does today. The universe contains many massive galaxies, fewer intermediate ones, and very few tiny luminous systems. This distribution reflects where growth succeeded and where it failed. 35 marks a boundary where failure becomes dominant. This boundary is not static. In the early universe, conditions favored star formation in smaller halos. As the universe evolved, that favor shifted toward larger systems. 35 formed at a time when the boundary was lower. Its present existence reflects conditions that no longer apply. Similar halos forming today would almost certainly remain dark. This time, dependence complicates simple scaling laws. One cannot define a single minimum galaxy mass independent of cosmic epoch. 35 demonstrates that galaxy formation thresholds evolve. Models must therefore track not only mass, but timing relative to cosmic events, such as reionization. The idea of galactic failure also clarifies the relationship between galaxies and dark matter halos. Halos are the fundamental structures. Galaxies are contingent outcomes. Most halos do not become galaxies in the luminous sense. 35 is a halo that briefly did, and then stopped. This perspective reduces tension between theory and observation. Simulations predict many halos. Observations find few small galaxies. The difference reflects failure modes rather than missing physics. 35 supports this interpretation by showing that halos can exist with minimal stellar output. It also informs expectations for future surveys. As detection limits improve, more 35-like systems may be found, but there will still be a sharp drop-off below certain luminosities. That drop-off reflects physical limits, not observational incompleteness alone. XXXV's failure to grow also explains its structural simplicity. Without ongoing star formation, mergers or gas inflows, there were no drivers of internal change. Its structure remained close to its initial configuration. This preservation allows astronomers to study early conditions, but it is also a direct consequence of arrested development. The chemical simplicity discussed earlier fits naturally into this framework. Limited star formation produced limited enrichment. Once growth stopped, chemical evolution stopped with it. The galaxy's chemistry froze alongside its structure. The concept of galactic failure also has implications beyond dwarf galaxies. It highlights how many evolutionary paths terminate early across cosmic history. Not all structures grow. Many stabilize, stagnate, or disappear. Recognizing these outcomes is essential for a complete theory of structure formation. XXXV therefore serves as a reference point for understanding the lower end of galaxy evolution. It shows how far a system can go before growth becomes impossible. It defines a stopping point rather than a starting one. This stopping point is as informative as any success story. It reveals the limits imposed by gravity, radiation, and feedback. It shows how finely balanced early galaxy formation was. Small changes in conditions produced vastly different outcomes. By studying 35, astronomers gain insight into why the universe did not fill itself with countless tiny galaxies. The mechanisms that halted 35's growth operated widely and effectively. The luminous universe we observe today is shaped as much by suppression as by formation. In this sense, 35 represents a failure mode that was common, not rare. Its rarity today reflects survival, not formation frequency. Many similar systems likely formed and then vanished or became completely dark. XXXV survived because it stabilized early. It lost gas, stopped evolving, and remained gravitationally bound. This stability allowed it to persist when others were destroyed. Its failure to grow became the reason for its survival. This paradox underscores the complexity of galaxy evolution. Growth is not always advantageous. At small scales, growth can lead to destruction through feedback and tidal interactions. Stagnation can preserve. 35 embodies this paradox. It failed to become a larger galaxy, but succeeded in enduring. Its long-term survival makes it observable today and scientifically valuable. By framing 35 as an example of galactic failure, astronomers gain a clearer picture of how structure formation operates across scales. Success and failure are not binary outcomes, but positions along a continuum shaped by physics and chance. XXXV sits at a critical point on that continuum. It shows how galaxies can form, stop, and persist. Understanding this path enriches understanding of all other paths. In the broader narrative of cosmic evolution, 35 represents a quiet outcome. It did not dominate its environment or transform its surroundings. It simply endured. That endurance carries information from an era when the universe was young and uncertain. Studying such outcomes completes the story of galaxy formation. It reminds us that the universe's history is written not only by its largest and brightest structures, but also by the smallest systems that nearly faded away. XXXV and the question of how many galaxies exist. XXXV forces a reconsideration of one of the most basic questions in cosmology: how many galaxies actually exist in the universe? This question appears straightforward, but it depends critically on how a galaxy is defined and what can be observed. Systems like 35 sit at the edge of both definition and detectability, making them central to understanding whether current galaxy counts reflect reality or only its brightest fraction. Traditional galaxy counts rely on visible light. Galaxies are identified through concentrations of stars, gas, or emission across the electromagnetic spectrum. This approach works well for large systems and even for most dwarf galaxies. It fails, however, at the smallest scales, where luminosity becomes sparse and uneven. XXXV demonstrates that a galaxy can exist with so few stars that it barely registers against the background of the sky. If 35 qualifies as a galaxy, then the criteria for galaxyhood extend far below what was once assumed. Its total stellar mass is minuscule, yet it is gravitationally bound, dark matter dominated, and dynamically coherent. These properties satisfy physical definitions of a galaxy, even though the luminous component is minimal. Accepting 35 as a galaxy expands the lower boundary of the galaxy population. This expansion has immediate consequences for galaxy counts. The number of known galaxies increases not by adding many bright objects, but by extending the tail of the distribution toward extreme faintness. Each new discovery near this limit suggests that many more such systems may exist, but remain undetected. The question becomes how steeply the population rises as luminosity decreases. Cosmological simulations predict a rapidly increasing number of dark matter halos toward low masses. If even a small fraction of these halos host stars at the level seen in 35, the total number of galaxies could be far higher than current catalogues indicate. However, observations suggest that star formation efficiency drops sharply at small masses. 35 represents a rare case where this efficiency was just high enough to leave a visible remnant. The balance between halo abundance and star formation efficiency determines how many galaxies exist in practice. If efficiency drops faster than halo numbers rise, the number of observable galaxies remains limited. If efficiency declines more gradually, the universe could contain vast numbers of ultra-faint galaxies. 35 provides a data point that helps constrain this balance. The challenge is that detection limits obscure the true shape of the faint end distribution. Surveys are incomplete at low luminosities, and the incompleteness worsens rapidly as systems become more diffuse. XXXV was discovered only because of targeted searches and refined analysis techniques. Many similar systems may lie below current detection thresholds. Distance amplifies this effect. Within the local group, ultra-faint galaxies can be resolved into individual stars, enabling detection through stellar overdensities. Beyond the local group, this approach fails. Systems like 35 would be invisible at even modest extragalactic distances. This means that galaxy counts beyond the local group likely miss the faintest systems entirely. As a result, galaxy counts derived from deep field observations at high redshift may represent only the brightest fraction of early galaxies. If early galaxies resembled 35 more often than larger systems, then much of early star formation occurred in objects that are now invisible to direct observation. This possibility affects interpretations of early cosmic light and structure formation. XXXV also complicates comparisons between local and distant galaxy populations. Nearby surveys reveal ultra-faint systems that cannot be detected at high redshift, while distant surveys detect luminous systems that may have no local analogues. Bridging this gap requires understanding how populations evolve and which systems persist. 35 provides a local example of an early type galaxy that survived without growing. The question of how many galaxies exist is therefore inseparable from the question of how many galaxies form stars. Dark matter halos are abundant, but galaxies in the luminous sense are conditional outcomes. XXXV demonstrates that the conditions for forming even a minimal galaxy are restrictive. This implies that the total number of galaxies, while larger than previously thought, is still far smaller than the number of halos. This distinction matters for cosmological accounting. When estimating the total number of galaxies in the observable universe, extrapolations often assume that the galaxy luminosity function continues smoothly to very low luminosities. Systems like 35 suggest that this extrapolation may overestimate galaxy numbers if star formation efficiency collapses rapidly below a threshold. On the other hand, the existence of 35 also cautions against overly conservative estimates. It shows that galaxies can exist at luminosities once considered impossible. The true faint end slope likely lies between extremes, rising steeply at first and then flattening as star formation fails completely. XXV also affects how galaxies are classified in simulations. Many simulated halos are labelled dark because they form no stars. The fraction of halos that produce XXXV-like stellar populations influences predictions for the observable universe. Matching this fraction to observations helps calibrate feedback and reionization models. This calibration has ripple effects. It affects predictions for satellite populations, stellar halo assembly, and the contribution of faint galaxies to early cosmic processes. If 35-like systems are common, they may have played a non-trivial role in early metal enrichment and radiation fields, even if their contributions were brief. The question of galaxy counts also intersects with philosophical definitions. If a galaxy contains only a few thousand stars, does it still count? Physically, 35 behaves as a galaxy. Observationally, it challenges intuitive notions of what a galaxy looks like. Accepting it as a galaxy expands the conceptual landscape of cosmic structure. This expansion is not merely semantic. It influences how data are interpreted and how models are built. The universe does not draw neat lines between categories. 35 occupies a transitional zone where labels become less important than physical behavior. From an observational standpoint, 35 suggests that current catalogues are incomplete in a systematic way. They favor compact, higher surface brightness systems. Diffuse, ultra-faint galaxies are underrepresented. Correcting for this bias requires assumptions informed by discoveries like 35. Future surveys will improve sensitivity and coverage, but they will still face fundamental limits. Confusion, background noise, and finite observing time will always restrict detection. Even with perfect instruments, some galaxies will remain invisible because they lack sufficient stars. 35 marks the lowest rung that can be climbed with light alone. This realization reframes the goal of galaxy counting. Rather than seeking a definitive number, astronomers aim to understand the distribution of outcomes. How many halos host stars, how many fail, and how this depends on environment and epoch. 35 contributes to this understanding by defining a successful but marginal case. The implications extend beyond astronomy into cosmology more broadly. Galaxy counts influence estimates of matter distribution, the growth of structure, and the interpretation of deep surveys. Misjudging the faint end population can lead to incorrect inferences about the universe's evolution. XXX therefore carries weight disproportionate to its size. It informs debates about abundance, efficiency, and definition. It forces models and observations to confront the limits of visibility and the conditional nature of galaxy formation. In considering how many galaxies exist, 35 stands as a reminder that the universe is populated by many structures that barely register as galaxies at all. These structures matter not because they are numerous in catalogues, but because they define where catalogues end. The question is not whether the universe contains countless galaxies, like 35. It is how many halos approach this threshold, and how many crossed it even briefly. 35 crossed it just enough to be seen. That fact anchors extrapolations and tempers speculation. Ultimately, 35 shows that galaxy counts are not just tallies of light. They are measures of physical thresholds shaped by gravity, radiation, and time. Understanding these thresholds is essential to answering how many galaxies the universe truly contains. XXXV does not provide a final number. It provides a boundary. Beyond that boundary lies darkness structured by dark matter, largely unseen. Within it lie galaxies, defined not by brightness alone, but by their ability to briefly ignite stars before the universe closed that door. In this way, 35 reframes the question itself. The universe may contain fewer galaxies than the number of halos suggests, but more than the number of bright systems implies. The truth lies at the threshold, where systems like 35 reside. Studying 35 brings that threshold into focus. It turns an abstract question into a physical one, grounded in observable reality. Through it, the question of how many galaxies exist becomes a question of how many could exist, given the constraints of the early universe. That question remains open, but it is now better framed. 35 ensures that it cannot be answered without accounting for the smallest and faintest members of the cosmic family. 35. Dark matter dominance and the limits of luminous traces. XXXV brings into sharp focus a long-standing issue in cosmology, the extent to which dark matter, rather than stars, defines what a galaxy is and how it behaves. In large galaxies, stars dominate what is observed and measured. Rotation curves, luminosity profiles, and chemical gradients are all derived from stellar light. Dark matter is inferred indirectly. In 35, this relationship is reversed. The galaxy's identity is defined almost entirely by its dark matter halo, with stars acting as sparse traces rather than structural drivers. Measurements of 35 indicate an extreme mass-to-light ratio. The total gravitational mass exceeds what can be accounted for by stars by orders of magnitude. This is not an unusual feature for ultra-faint dwarf galaxies, but 35 sits near the extreme end of this spectrum. Its stars contribute almost nothing to the overall gravitational potential. They orbit within a dark matter framework that dominates every aspect of the system's dynamics. This dominance has practical consequences for how the galaxy evolves. Stellar feedback, which can reshape gas distributions and influence dark matter profiles in larger systems, has limited impact in 35. The stellar population is too small and too short-lived to significantly modify the underlying halo. As a result, 35 likely preserves a dark matter distribution close to its original state. This preservation is scientifically valuable. Many theories of dark matter predict specific density profiles at small scales. In larger galaxies, these profiles may be altered by baryonic processes. In 35, such processes were minimal. The galaxy therefore offers a rare opportunity to study dark matter behavior in a regime where baryonic interference is weak. The nature of that dark matter profile is central to debates about dark matter physics. Cold dark matter models predict cuspy density distributions toward halo centers. Alternative models, including warm or self-interacting dark matter, predict flatter cores. Observations of 35 and similar systems are used to test these predictions, although uncertainties remain significant due to limited stellar traces. The challenge lies in extracting robust conclusions from sparse data. With so few stars, velocity measurements are difficult and sensitive to small number statistics. Individual stellar motions can disproportionately influence inferred mass profiles. Careful modelling is required to avoid over-interpreting noisy data. Despite these challenges, 35 consistently appears to require a substantial dark matter component. No alternative explanation, such as tidal inflation or observational error, adequately accounts for the observed dynamics. The galaxy is gravitationally bound and stable over long timescales, implying a deep underlying potential well. This raises a conceptual question about galaxy definition. If stars are merely passengers within a dark matter halo, does the halo itself constitute the galaxy? In 35, the answer appears to be yes. The dark matter halo is the primary structure. The stars are incidental but informative. This perspective aligns with theoretical models in which dark matter halos form first and baryons populate them conditionally. 35 represents a case where the halo formed successfully, but baryonic participation was minimal. The galaxy's existence therefore reinforces the idea that dark matter sets the stage, while luminous matter plays a variable role. The dominance of dark matter also explains 35's resilience. Tidal forces from nearby massive galaxies can disrupt stellar systems, but dark matter halos provide protection. 35's halo appears sufficient to prevent complete tidal dissolution, even if some mass loss occurred. This protection helps explain how such a fragile-looking system survived for billions of years. At the same time, dark matter dominance limits internal evolution. Without significant baryonic mass, there is little to drive structural change. No disk forms, no spiral structure emerges, and no central concentration develops beyond what the dark matter itself provides. The galaxy remains diffuse and static. This static nature contrasts with the dynamic evolution of larger galaxies. It suggests that below a certain baryonic threshold, galaxies become dynamically frozen. Their subsequent history is one of passive orbiting rather than internal transformation. 35 exemplifies this regime. The implications extend to how dark matter is detected and studied. In most galaxies, dark matter must be inferred by subtracting baryonic contributions from observed dynamics. In 35, the baryonic contribution is negligible. The observed dynamics are effectively pure dark matter signals. This simplifies some analyses while complicating others due to limited data. XXXV also informs discussions of dark matter substructure. Cosmological simulations predict that large halos contain many smaller subhalos. Systems like 35 may represent luminous counterparts of some of these subhalos. Their properties help bridge the gap between simulations and observations. This connection is particularly relevant to the so-called missing satellites problem. Simulations predict more small halos than observed dwarf galaxies. XXXV supports the idea that many halos exist but host very few stars. The apparent mismatch arises because most halos are dark, not because simulations overproduce structure. By anchoring the luminous end of this hidden population, 35 provides a reference point. It shows how little stellar mass is required for a halo to be detectable. Below this threshold, halos remain invisible to current instruments. The dark matter dominance of 35 also affects its interaction with the surrounding environment. Gas accretion is suppressed not only by shallow potential depth, but also by the lack of cooling mechanisms driven by stars. Without stars to enrich gas with metals, cooling remains inefficient. Dark matter alone cannot compensate for this deficit. This reinforces the self-limiting nature of small galaxies. Once star formation fails to reach a critical level, the conditions required for future star formation become increasingly unfavourable. 35 entered this feedback loop early and never escaped it. From a broader perspective, 35 illustrates how dark matter shapes the lower boundary of galaxy formation. It defines the minimum conditions under which a galaxy can exist as a luminous system. That minimum is determined not by dark matter alone, but by the interaction between dark matter and baryons. The study of 35 therefore informs both astrophysics and fundamental physics. It constrains how dark matter behaves at small scales and how baryons respond to it. These constraints feed back into models of cosmic evolution. XXXV also highlights the limits of using light as a tracer of mass. In this regime, luminosity becomes an unreliable proxy for structure. Galaxies may exist that are almost entirely dark, with only faint stellar signatures betraying their presence. Recognizing this limitation shifts observational strategies. Rather than searching only for light, astronomers increasingly look for dynamical effects, stellar streams, and subtle perturbations that signal dark structures. 35 validates this approach by demonstrating that some galaxies are barely luminous at all. In theoretical terms, 35 challenges any model that ties galaxy identity too closely to stars. It shows that stars are optional components, not defining ones. The defining element is gravitational coherence, provided primarily by dark matter. This understanding aligns with a hierarchy of structures in which halos are fundamental and galaxies are emergent. 35 sites near the bottom of this hierarchy, where emergence is minimal but still present. The dominance of dark matter in 35 therefore reframes how small galaxies are interpreted. They are not failed versions of larger galaxies. They are systems operating under different physical regimes, where dark matter dictates outcomes almost entirely. In this regime, traditional galactic processes lose relevance. Concepts like star formation efficiency, metallicity gradients, and stellar feedback become secondary. The primary question becomes whether any baryons remain bound at all. 35 answers that question narrowly in the affirmative. A small number of stars remain bound, orbiting within a dark halo that defines the system. This narrow survival defines the galaxy's character. By studying such systems, astronomers gain insight into the threshold where light gives way to darkness. 35 marks that threshold clearly. It shows how galaxies fade into the dark matter landscape that underlies all visible structure. This landscape is vast and mostly unseen. 35 offers a glimpse of it through a handful of stars. Those stars are not the story themselves. They are markers of a deeper structure that dominates the universe. Understanding that structure is essential to understanding cosmology as a whole. 35 contributes to this understanding by revealing how little light is needed to signal the presence of a galaxy. In doing so, it shifts attention away from brightness and toward mass. It reminds us that the universe's most important structures are not always its most visible ones. XXXV and what the smallest galaxies reveal about the universe. XXXV ultimately forces cosmology to confront a foundational issue that extends beyond any single object. What the smallest galaxies reveal about how the universe organizes matter, limits complexity, and preserves information from its earliest epochs. While large galaxies dominate attention because of their visibility and scale, systems like 35 provide a complementary perspective. They expose the minimum conditions under which structure can exist and persist over cosmic time. At its core, 35 is evidence that galaxy formation is not a guaranteed outcome of structure formation. Dark matter halos form abundantly across the universe, but luminous galaxies do not. The conversion of a halo into a galaxy depends on a delicate balance of mass, timing, environment, and feedback. 35 exists because it briefly satisfied these conditions, then fell below them. That transition is as informative as continuous growth. This perspective reframes the narrative of cosmic evolution. Instead of a smooth progression from small to large structures, the universe appears to be shaped by thresholds. Below certain thresholds, complexity stalls. Above them, it accelerates. 35 sits near one of these boundaries. Its properties encode where that boundary lies and how sharply it operates. One of the most significant lessons from 35 is that early success does not imply long-term growth. The galaxy formed stars, assembled a coherent structure, and then effectively froze. This outcome contradicts assumptions that early formation naturally leads to later dominance. In reality, early formation can just as easily lead to early stagnation. This stagnation preserves information. Because 35 experienced minimal subsequent evolution, its present state closely reflects its early conditions. Larger galaxies erase their origins through mergers, star formation, and internal restructuring. 35 did not. It retained signatures of early universe physics that are inaccessible in more complex systems. These signatures include its chemical simplicity, its dark matter dominance, and its lack of internal differentiation. Each of these traits reflects constraints imposed during formation rather than outcomes of later evolution. Studying them allows cosmologists to test models of early structure formation under relatively clean conditions. XXXV also illustrates the importance of survival bias in the observed universe. The systems that persist to the present are not representative of all systems that formed. Many small galaxies likely formed and were destroyed or rendered completely dark. 35 survived because it stabilized early and avoided catastrophic interactions. Its existence therefore reflects not just formation, but endurance. This endurance reshapes how rarity is interpreted. 35 is rare in observations, but that does not mean it was rare in formation. It may be one of the few survivors of a much larger population. Understanding this distinction is essential for interpreting the fossil record of galaxy formation. The galaxy also demonstrates that minimalism can be stable. There is no intrinsic requirement for ongoing star formation or complexity to maintain structural integrity. A galaxy can exist as a gravitational system with very little luminous matter, provided its dark matter halo remains intact. This challenges assumptions about the role of stars in defining galaxies. In 35, stars are witnesses rather than drivers. They trace the potential well, but do not shape it. This inversion emphasizes that galaxies are fundamentally gravitational structures, not luminous ones. From a theoretical standpoint, 35 constrains how models handle low-mass halos. Any viable model must account for the existence of such systems without overproducing them. It must explain why some halos host stars briefly, others not at all, and why only a few survive as faint galaxies today. These constraints ripple outward. They affect predictions of satellite populations, the buildup of stellar halos around larger galaxies, and the interpretation of faint background light. Each of these phenomena depends on how small systems form and evolve. XXXV also informs debates about the early universe's energy budget. Small galaxies may have contributed to early radiation fields, chemical enrichment, and feedback processes despite their limited mass. Even brief episodes of star formation can have disproportionate effects when many such systems exist. At the same time, 35 demonstrates the limits of that contribution. Its short star-forming phase and small stellar mass suggest that ultra-faint systems were not dominant drivers of long-term cosmic evolution. Their role was localized and transient. This balance helps refine models of early cosmic history. It suggests that while small galaxies participated in early processes, larger systems ultimately shaped the universe's large-scale structure. XXV represents the lower boundary of that participation. Another lesson lies in observational methodology. Discovering and characterizing 35 required targeted strategies, careful analysis, and theoretical context. Such systems do not announce themselves. They must be inferred from subtle signals. This underscores how much of the universe remains hidden simply because it is faint. As observational capabilities improve, more systems like 35 may be found, but they will always be difficult to study. Their importance lies not in their numbers, but in the constraints they impose. Each new example refines understanding of where galaxies end and dark halos begin. XXXV also highlights the role of chance in cosmic history. Slight differences in environment or timing could have prevented its formation entirely or allowed it to grow larger. Its present state is one realization among many possible outcomes. This stochasticity complicates deterministic narratives of galaxy formation. Recognizing this randomness does not weaken cosmology. It strengthens it by aligning theory with observed diversity. The universe produces a wide range of outcomes from similar initial conditions. 35 is one such outcome, preserved long enough to be studied. In a broader sense, 35 reinforces the idea that the universe retains memory unevenly. Some systems continuously overwrite their past. Others preserve it almost unchanged. Both are necessary to reconstruct cosmic history. Without systems like 35, early conditions would be far harder to infer. The galaxy therefore serves as a bridge between theory and observation. It connects abstract models of early structure formation to tangible, observable remnants. This connection grounds speculation and sharpens predictions. XXXV also reminds cosmology of its limits. Even with advanced instruments and simulations, some questions remain unresolved. How many such systems exist? How many formed and vanished? How close is 35 to the absolute minimum galaxy? These questions remain open. What 35 provides is not final answers, but boundaries. It defines what is possible. It shows how little is required for a galaxy to exist and how easily growth can halt. These insights shape how future discoveries are interpreted. The study of 35 also has implications beyond galaxies. It informs understanding of dark matter behavior, the efficiency of baryonic processes, and the interplay between gravity and radiation. Each of these themes extends into other areas of astrophysics and cosmology. Ultimately, 35's significance lies in its scale. By operating at the smallest end of the galactic spectrum, it exposes processes that are masked at larger scales. It simplifies the problem by stripping away complexity, leaving core physics visible. This simplicity does not make 35 less important. It makes it more revealing. In its faintness and restraint, it offers clarity. As cosmology continues to advance, systems like 35 will remain reference points. They anchor theories, test assumptions, and remind researchers that the universe is shaped as much by what fails to grow as by what succeeds. XXXV does not resolve debates about galaxy formation. It reframes them. It shifts attention from growth alone to limits, thresholds, and survival. It ensures that the smallest galaxies remain central to understanding the universe as a whole. In that sense, 35 is not merely the smallest galaxy. It is a measure of how far structure formation can go before complexity stops. That measure will continue to guide inquiry as new observations push deeper into cosmic history. The universe's story is incomplete without its smallest chapters. 35 ensures that those chapters are read, not overlooked.